Okay, so today we're going to start off by talking a little bit about the light transport that's going on in Handmade Hero right now, because I think, I don't work on Handmade Hero at any time other than on stream, right? So although people apparently think I do, which is very interesting, I've noticed there are threads on things like Hacker News where people post ridiculous theories that are like, no, Casey works on it all the time. Literally, you've watched me do the whole thing on stream, and anybody who's been here every day knows there's literally no change to the code base. And you can even go to GitHub and see each change with the days marked on it. But, that's too much work for people on Hacker News. They'd rather just post their idiotic opinions to a giant thread full of nonsense. So anyway, today we're going to look at light transport in Handmade Hero. Since I don't work on it during the week at all, and we only have 2 hours or 3 hours on Sundays to do it, in general, I find that sometimes during the week, like, my brain will be thinking about it, though. Like, I'll be like, oh yeah, last Sunday we did this thing, and I'm like, I just realized I screwed something up, right? You've seen me do that on Handmade Hero before. We'll start, and I'll be like, I was thinking about X, and I think we did a stupid thing or whatever. And so last week we got the lighting to a really good place. It looks really awesome right now, but it's still got some bugs in it. I'm quite sure that we've got some bugs in it we got to fix. Some of them are obvious, some are probably not so obvious. And so what I wanted to do here was kind of go over something I was thinking about during the week. I was like, I don't think our light transport is actually correct right now. Our thinking about light transport isn't correct, and I think that's where the blossoming bug is coming from. We fixed some of the egregious errors in the blossoming bug. Those were because you were able to transport light in ways that you shouldn't have, because we lost the Z bounds. You saw me fix that on last week's stream. We kind of discovered that's what was going on, and that's all fine. But I think we still have a fundamental error in how the light transport is working, and I think that's what causes that sort of, if you put a powerful light in a place, you get this blossoming effect. I think that's actually not a bug in our code. I think that's a bug in our actual equations, meaning the code is correctly simulating what we told it to, and there's not a typo or a missing minus or that kind of thing, like a bug in the code implementation. There's a bug in the concept. The way we are doing things has a missing piece to it, I think. And again, this is just what I thought this week, kind of as it was kicking around in my head, so I haven't actually looked at it. I could be wrong, but I wanted to go over what I was thinking of and explain it, and sort of also work through it myself, so that I could see if I think I'm right or not, right? Because it was just kind of kicking around in my head. So right now in Handmade Hero, I want to go over the first part of the light transport, which is what happens when you throw a light source in a scene, and why I think that's roughly correct. And then I want to go over the second part of light transport and explain why I think it's roughly wrong. So what happens in Handmade Hero right now is that if you imagine a top-down view, which Handmade Hero kind of is, it's a bit 3/4 or whatever, but you can sort of see it's mostly meant for kind of looking down on things, like a doll's house kind of doll's house is probably more straight on. So maybe more like old school, Ultima style kind of a thing. Anyway, when you look at what happens, we don't have really a concept of light sources in Handmade Hero, because the idea was we wanted the lighting to be very diffuse and sort of expressive and soft. So we don't specifically earmark light sources and treat them differently than anything else. Anything in the world can be a light source, and it's fully globally illuminated, but there still is the concept that light has to come from somewhere. So, if nothing in the world was emitting photons, it would be completely dark, right? Something has to start by emitting the photons. So we do have the concept in Handmade Hero of setting a thing to have an emissive material, right? To be able to emit photons, and that's where the lighting starts. So even though we don't specifically say, oh, let's count the light sources, how many there are, because that's one way to do a system, right? Systems that are less global illumination based will oftentimes talk about, okay, we allow 50 light sources per voxel cell, that we illuminate, and we do the equations for all of them inside a shader. There's ways you can think about light sources as a first-class citizen. We just don't do that in Handmade Hero. But the fundamental concept that light has to come from somewhere is still obviously going to be inherent in the system. And so if you put something in, like a block, that has an emissive property, then that is going to shine light into the environment. And how does that actually work? Well, we have light probes, right? scattered throughout the environment. At the moment, they're regularly spaced. The reason they're regularly spaced is because we wanted it to be relatively straightforward to sample them in the shader. So when we do our actual pixel shading, we wanted there to be a pretty clean, simple way for us to interpolate the lighting in the world. So we have, regularly spaced light probes. And the way that the light would be gathered from this emitter here is that any given one of these light probes will be sending out a series of sample rays on every frame, right? And these sample rays are distributed across a sphere. And they're relatively stochastic, so it's actually white noise sampling right now, which is not the best sampling. We had blue noise in there, but we actually changed to dynamically generating samples, and we haven't tried to do something where we can quickly dynamically generate blue noise. We probably should. That's like something that would improve our sampling, so at some point we probably should do that, but right now we're not actually doing that. And I think that adds more noise. So when we're looking at kind of the final cleanup pass after we get all these bugs worked out, that would be a good thing to add. But again, all that's going to do is add some extra noise. Using white noise instead of blue noise is going to mean our sampling's a little bit less clean probably. But other than that, there's no difference between white noise and blue noise in terms of like bugs. Like the light transport equation should still work with white or blue noise. You shouldn't end up with like dramatically different results in the actual answer. It's just going to be a little more noisy. So when we send out a ray, sometimes one of these rays hits the emitter, and that will add that light proportional to how many rays we cast. It will add that light into that sample of our outgoing light map. So we have a light, basically that light probe has some number of samples that it's keeping for lighting, and out of each one of those sample regions, it sends lots of rays, and then it sums those up and divides by the total number of rays set to figure out how many are in there. And again, that's not particularly great sampling either. There's potentially ways we could improve that as well to get less noise. I'm not really very knowledgeable about sampling theory, so that's why we haven't rolled anything in there yet, is because I don't know, I really don't even know how much better it could be or if it's worth it or anything like that. People who are really good at sampling would kind of know just right off the bat, what they should probably do in there. But, I don't have any expertise in that area. So that's why we're just kind of randomly just averaging them, right? But you could probably do better things than that based on knowledge of certain probabilities and things like that. If you go look at high-end rendering papers, they're typically not going to do something like averaging. They're typically going to use some kind of probability distributions to reduce the amount of noise in the system or who knows what, right? So, again, just pointing out that there's things in here that aren't fantastic, but they're not necessarily buggy. Like, they're still going to produce reasonable answers. They're just not maybe going to be as noise-free as they should be with the number of samples that have been taken. Now, you may wonder, well, how does this, if we're just sending out these samples and then we're basically just writing this light back in there averaged, is that reasonable light transport? And my argument is for this first step, it actually is reasonable light transport. And the reason that I say that is because these sample rays, if you notice, they do exactly what you would expect photons to do if they were going in the reverse direction. So, for example, if we were going to try to shoot photons out of here, and we're talking about, fundamentally when we're talking about light transport, what we want to think about, or at least one way to think about it, is if we're shooting all these photons out of a light source, the results that we get for lighting should roughly match what we expect to happen if we had tons of particles leaving this light source. We shouldn't end up with answers that are fundamentally different from what would happen if we shot out particles from this light source. So if we shot out particles from this light source, what we would expect to happen is they would land at these sample points, right? They would arrive at these sample points proportional to some kind of an inverse square law, right? Because as you send particles out in random directions from a light source, like a light emission photon, like photons from a light emitter would do, we expect them to get less concentrated as they get further away. So in a ring right around the light source, the photons are very concentrated on that surface. As that ring gets further out, the photons will be less concentrated. Why? Because for any two randomly picked directions, the further out I look at where the photons go, the more gap there is between them, right? So no matter how dense they are at the emitter, As I get out to one ring, well, they're less dense now. As I get out to another ring, they're less dense now, right? And they're going to be less dense in 3 dimensions based on the inverse square law. Why? Because they are actually going, a surface of a sphere is 2-dimensional. So any paths on that sphere will get bigger as a proportion to the square of the radius, because the surface area of the sphere gets bigger as proportional to the square of the radius. So this convection process here, where we're pulling light, is going to work exactly the same way. Because the rays diverge as they get further apart, in exactly the same way that the outgoing rays would diverge from the emitter, we're going to get a naturally inverse square fall off of light arriving at any given point for the exact same reason. So the inverse square law is actually already captured in our light reception in exactly the way that it should be, meaning any particular direction will simply have less light contributing to that as it gets further away, because the rays will be less likely to hit, right? So it's naturally going to capture inverse squared fall off from that, and furthermore, it's better to do it that way because if you happen to have a large light source, right, for which all of these, all of the rays going out of one, little region, if they all would have hit that, you don't want to do something like apply the inverse square law manually, because light doesn't itself fall off with an inverse square, meaning an individual photon carries exactly as much energy across the entire line as it did when it left, right? It doesn't change its energy amount. So the reason you get an inverse square law fall off from light ever is strictly because there's less area that the photons are falling on as you get further away. But if you actually do have a light source so large that all of the photons are dense enough that they're all still going to hit, you should still capture the full energy of the light source in that patch. So you don't want to artificially apply some kind of weird inverse square law fall off that you just pulled out of thin air, right? Because you really do want to measure how much of the light source you're actually seeing, and that's how much energy you should be getting. You don't want some additional inverse squared fall off that's just based on distance, because it's not really the distance, it's the surface area of the projection of the light that's causing that feature. I don't want to say anomaly. It's not weird. That's causing that aspect of lighting. So in my opinion, I don't think we have a problem here. That is generally what should happen. The only thing I would say is right now we don't have any real understanding of what our light source's value actually is. We just say stuff like, oh, the emission of this thing is 5.0, right? And we don't know what that value is. Now, it's okay that we don't know what that value is because we're not trying to simulate a particular real environment. Like if you were doing, some kind of architectural rendering, it may be very important for you to actually know, okay, this is going to be in candelas or looms or whatever, however we're specifying. We get some manufacturer's explanation of how their fluorescent light bulbs work, and we know that we're going to put those into this house, and we want to see how the lighting actually works. So we need to know, right, exactly how much light is being put in here, and we need to simulate that light. Things like Maxwell Render or those kind of things that are designed to give you accurate results for architectural previds, they shouldn't be using a value like 5.0 because it doesn't mean anything, right? They can't correspond it to something in the real world that they're actually trying to simulate. But it's fine for us to say 5.0 because we only have to tune things relative. We might want to make that more concrete in the future if our goal is to make it easier for us to sort of specify real-world lighting conditions, like, okay, the sun's this bright, a light bulb's this bright, and we correspond those to some real-world values so that it's easier for us to balance. You might want to do that in a game. For our game, it doesn't seem like we're it's a very fanciful game. The art is kind of hand-drawn and cartoony. So, we probably never need to move past this understanding of lighting. But the point is, we don't know what that value is. It's just an arbitrary value that we plucked out of thin air, and we can keep going with that. We don't have to, but it's worth noting that nobody has spent any time determining what that value actually means, so we don't have a way to tie it back to anything. And that's one issue you might want to address depending on what you were doing. I don't think we need to, but, you could. So this entire thing, I think, is fine. I don't actually think there's any problems in here, and I don't think that we would have any real issues with it going forward, because I think we could just tune these values. Once we put in maybe an exposure equation on the back end, the exposure equation and this can just be arbitrary, and we tune them with each other, and then we're good, right? It's just a tuning process to get a look that we want. When we're happy with the exposure equation and the lighting values, we just call it that's what it is, and then we know, our bright lights are 10, our dim lights are 2, and that's it, right? So that's totally fine for an artistic process. We don't need to correspond these to real-world values because we're not actually trying to produce anything that matches something in the real world, so it's not going to really be much of a hindrance to us unless we just find that tuning them is too difficult and we'd rather, pull some real world values out so that we can just put them in directly and, not have to tune, right? That's another thing that you can get. But I don't even know if that would work because when you're talking about cartoonish art, you wouldn't necessarily know. You're like, you put in these values that are from the real world, it might look terrible, right? Because, it's artistic and the lighting's going to have to be not that real because it's going to have to go with the, the sort of cartoony feel. All right. So that I think is fine, but I think we have a problem in the other part of the way we're doing light transport, and so that I'm fairly comfortable that we're not doing something dumb with that light sampling when it comes from an actual light source. It feels about right, and furthermore, I think that would be true for anything else. Meaning, in other words, if you're pulling light from just reflective surfaces, I think that inverse square part works just fine as well. But let's talk about the part that I think is not correct here. So let's suppose that we talk about a reflective surface instead, okay? Because we have other cases, excuse me, in the world where you can gather light. Like I said, we actually don't treat light sources any differently from anything else in Handmade Hero. Everything is basically capable of reflecting light. It's straightforward, unbiased global illumination. Everything just is able to send light, so we don't have any kind of concept of something being a light source or not, other than when you hit it, it's able to generate photons out of thin air. It doesn't have to reflect them. That's the only thing that differentiates an emitter in our system. What that means is that when you look at our light probes, yes, we have an emitter, like so. And what will happen is when you are looking at the first time that emitter has ever been hit by anything, the inverse square law applies. So, we get this sort of thing happening here, and proportionally less of the rays, from here will hit than here. So the light will be dimmer here than here for that reason, right? Less light will be captured in this light probe, so it will naturally have an inverse square fall off as it goes. But what we do not do right now is differentiate between an emitter and a reflector in terms of the energy that's being provided. So, if we look at something like a surface in the world, and we say, okay, what happens when we have a surface like this, and somebody hits that surface as a sample point? Yes, the inverse square law will apply, meaning I am less likely to hit that point on the surface with rays, or that small region of the surface with rays as they go further out. That's true. But what happens when I sample from here is I take the reflectance of this surface, which is something, right? Like we'll have a reflectance number of, 0.7, 0.7, 0.7 or something for like a sort of diffuse but fairly reflective surface. It just has some, we're literally in there just multiplying by a modulation, right? So we hit this thing. What we do is we sample from the nearby light probes. So let's just say that this one is mostly dominant here because we're close to it. It doesn't really matter. What we get is we look at, okay, we're trying to figure out this particular light probe, how much exits in this direction from this light probe, because we're like blending a bunch of these together, right? And we send that amount back, right? We're basically just saying, like, look, this is how much light would go out in that direction. So the thing that I was thinking is probably wrong here is that at no point do we ever actually try to differentiate between light that's being reflected and light that's being emitted. What I mean by that is that the emitter is itself something that generates photons. So anybody who is looking directly at the emitter obviously is going to get some number of photons given by that brightness level, right? Like 5.0, whatever that is. We don't know what that is, but it's abstractly some measure of the density of photons that are going out, right, per unit area on that, on the emission of photons in a sphere as they, go out into the world. Anyone who hits it, we don't have any concept of like bias in light direction. We could introduce it, but we don't right now. So the entire sphere is just covered with this density of photons. And I think that's sampled roughly correctly. Because of that inverse square fall off of the sampling rays, you will naturally get less as you go further out. So you'll be less likely to hit the light source as you go further out. So that seems fine. But what doesn't seem fine is that when you get those results, so I hit this thing and I say, oh, I sampled this, and what I see is that in coming out this direction, right, I'm going to look back in the opposite direction and see how much stuff that I hit. So, maybe this is not quite right. Maybe I should be talking about this so that it would be hitting this more directly. What I will get is basically that the inverse squared fall off from this light at this point will be sent completely along this ray again, like a repeater, right? Because at no point did anything other than this reduce the light amount. Does that make sense? At no point did we ever say, oh, by the way, the light that falls incident to this has to be radiated out without adding energy, right? Meaning all of the light that we're going to receive at a particular point, we can't radiate out more than we actually got. So let's say, for example, that at this particular point, right, when we cast in these directions, we got a certain amount of light energy. Well, everybody who roughly hits from that area will be getting that same light energy sent to them. But that, and again, this is, I'm really not knowledgeable in this area. I think I tweeted when I tweeted out, I was like, it's too bad Don Mitchell is not here to explain this to us because, I just fundamentally don't really get light very well. I think one of these days I probably should write like a full like photorealistic ray tracer to get my head fully around how you actually think about light. The phrase watts per steradian, right, should be coming up here, and I should have a lot more of a handle on like what's actually happening quantity-wise. So I don't pretend to be very good at this stuff because I simply never have worked with it long enough to really get good at it. And so it's a bummer. And one of these days I need to fix that. That's for sure. Before I'm, 60 or whatever, I need to sit down and actually do that. But in lieu of actually having someone with really hardcore rendering expertise or ray tracing expertise, I'm simply going to try and point out that I don't think we are properly accounting for the fact that a given surface can only reflect the amount of energy it received and toto, less its modulation, meaning like after it takes away the 30% or whatever of light that it's absorbing, right? The remaining 70% of the light that it captured, that light has to go out based on some distribution. It can't have every direction receive the entire amount of light that it received from the opposite direction, right? Because if you allow that to happen, then what you're going to get is exactly the bug that we see, which is that on the first frame, everything's fine because you only are sampling from these light sources and each probe just got the distribution from the light source, and that's fine. But if you keep the light source in one place, it will then basically contaminate as it spreads outward because each reflector is basically capable of reflecting the total energy of the light source again. So yes, it inverse squared fall off, right, when it got from here to here. But then on the next frame, this is capable of picking up basically the entire light source again and moving it one probe forward, right? Because we're not accounting for the fact that it shouldn't be able to distribute that entire light that it received. It should only be able to distribute that light proportional, it should only be able to redistribute that area across the entire hemisphere, which means some of it goes back in the other direction, right? And so on. So I think what's basically happening right now is our light probes are functioning like mirrors. They're like one frame delay mirror. So rather than the light itself actually getting distributed and sent along, it's actually kept and propagated entirely from light source to light, from probe to probe as we go. And calling them mirrors is wrong. It's not even mirrors, they're replicators, right? Because not only a mirror would just send it on its way and not keep it. They're worse than mirrors, right? They're mirrors that send all the light out in the same direction again, so it's just like bucket brigade, but also they keep it, so they show up bright as well. You know what I'm saying? And so it's this lack of a reflectance equation happening at the point that distributes the energy fairly and without adding energy that I think is our problem. I hope that makes some sense. That's just my way of saying why in my head I think the behavior we're seeing of that light contamination is exactly what we actually should expect because of the way that we are sampling, right? We are not sampling the reflectance in a way that actually conserves the energy that is incident to the point, right? So that's my assumption, and I could be wrong, but that's my assumption. And so I think what we're doing wrong here is we are doing something when we actually go to sample. So, I'll draw it down here because I've drawn too much crap up there. So imagine we have like some close samples like this. We don't really in the game have this, but I just want to make it a little simpler on us. So suppose we have some samples here. And we are going to do something where we say, okay, we're sampling from this ray. So this guy, is sampling basically the light that's coming in this direction so it can update this light probe. And let's suppose, so that's going to send out a probe, in this direction or something. And so let's say there's a wall, here, and this is going to hit that wall, right? And so we're going to have something like this. Or maybe let's make it even simpler. This is an emitter, so we'll just do one bounce, right? So what we would say is, okay, this emitter, right, we have some density that we sampled at this emitter, and out of this direction, which is the direction we're going to sample, we have some amount of emission coming in here, right? Now, for this surface, what we want to say is if it's, whatever this surface's value is, we're expecting to send light back out into the environment at like a 70% rate. So we know that whatever comes in here, we have some total amount of energy that's sampled out of this, particular thing, and we know that we're going to send 70% of it back out, right? So I would assume, although I guess I don't, and this is the part where it's very tricky for me to think through. So if we're going to send 70% of it back out in this direction and keep 30% of it here, right? the 30% is just gone. This just disappears, right? It can't be seen. It's just absorbed into the material as heat, or I don't even who the heck knows. That's actually like, welcome to material science. I have no idea what's going on there, right? But some amount of the photons are just like absorbed and do quantum things and convert to IR, or I don't know what they do. So some amount of the photons are just absorbed. 70% of them have to go back out into the environment. And so, 70% of them are going to go out in some kind of a ring. The problem that we're having here is when they hit other light probes, like these light probes in the environment. What I don't quite understand is, should these light probes, how should these light probes react to capturing that 70%, right? That's the part that's very confusing to me. So we do want 70% to go out here, but we don't want we don't want all three of these, for example, if they all happen to fall within the texel of that octahedral map. We don't want all three of these to all have 70%, right? They each would need to get a proportion of the 70%, I think, meaning that the photons that come in here, however many you got, they can't all go to each, right? Each light probe has to capture exactly a third, or maybe these would capture less because they're further off angle. I don't know. But the total light energy that comes in here on that arc, that's the reflected angle, that solid angle. The outgoing solid angle has to distribute that, I would think, fairly. So it should have to do something like, 20, 20, 30, right? And right now, I think it'll just get 70, 70, 70, which is, I think, where our light contamination comes from. My naivete, and the reason that I'm saying that I'm not comfortable with this stuff and I don't really understand it, is that although I'm saying that, I don't really have a solid understanding for how you'd actually write the equations for that. Partially because light probes are weird. They're not surfaces. They're kind of just things floating in space that measure the light that goes through them. So I'm not sure exactly how that would work. Because these do have inverse squared fall off because of the way they back sample, right? They're sending out samples, and that averaging process will knock down the amount based on how many hit. And so should that naturally produce the 20, 20, 30, right? And right, I don't know. Maybe I'm not explaining my confusion very well. So I apologize. But if my argument is correct that just by sampling this, you're going to get less sampling as it gets further away, you would expect that to have the inverse square coverage. It tells you what's coming in. The same argument should sort of apply here. I mean, shouldn't it? But I guess I don't know. I don't know if there should also be this particular thing. When we sample in the reverse direction, I don't know if we should divide by the surface area again. I don't know whether we would divide a second time. Maybe I need to try and think about this in terms of individual photons. Because, it could be that actually this number, because there's some number here, that this already has that surface area division effectively baked into it, meaning because we can set this to whatever we want, and it's just an arbitrary brightness value, it could be that actually, no, when you hit here, you should have said how big does this ray actually represent? And we're actually going to count that many photons, right? Because it's sort of a sample that's a part of that's sort of trying to reconstruct how many photons were actually incident. And this could sort of just have that baked in implicitly in the number. So, you're never going to see that bug. I mean, it's not a bug, but you're never going to see that aspect of your system. You wouldn't think about it. So it could be that in this case, you actually do need to do that. And maybe we can look and see. Let's think about this. Maybe we can look and see if we actually do a little photon counting exercise, if we can convince ourselves one way or the other about that. I'm going to take a drink of water. Hold on a second. Someday we're going to have technology for this. I mean, we already have probably the technology. It's just nobody's building them. For instant erase light boards. And that will be a very good day. When these are just like LCDs, right? And the pen is actually just like a Wacom pen, basically, that lights the surface, that tells the LCD to like solidify there. Someday. Or we'll just all be in Mark Zuckerberg's horrible metaverse or something. But of course, in that case, none of this stuff would work. It'd all just be buggy and showing you ads all the time. So that probably wouldn't solve the problem. All right. That didn't take too long, though. Okay, so let's just count. Let's do some like basic photon counting. And again, this is just for my own purposes to try and like think through what's happening in this situation so that I could figure out like where in the equations, we have very simplistic equations right now. We're hardly doing anything during light transport. And the question is like, what would we add? If I'm right that this is erroneous, meaning we're getting light replication because we're missing a surface area divide, right? And just to be clear, when you reflect things off a surface, you also have like a cosine fall off and things like that. I'm not talking about that. I'm not talking about trying to condition the fall off. I'm talking about no matter what we do, how do we ensure that the energy transfer is correct, right? So because any surface reflectance function you might want, we should be able to, whatever the equation is we choose, even if it was just purely like it's perfect rate, like it's not even cosine fall off, it's perfectly distributed. If that's what we for some reason wanted, we should still be able to condition the equation so that you don't get feedback, right? We should be able to condition the equation so that there isn't like an energy buildup happening. So let's just try some photon counting and see if there's something to be said about that. So let's suppose that we start with a light source, right? So our emitter is going to emit some number of photons out from its surface, and we have our collection point. So here's our probe. This is going to be our probe P. And our probe is basically like going to hit like so. And let's suppose that we say that because we're basically trying to simulate a large number of photons with a few rays, right? So each one of these hits is going to be some number of photons comes back, right? And I guess I would say right now, if we had to categorize what our actual light values are, that's what they are. They're basically like a one-ray photon count. So 5.0 is like the photon count, right? So when we hit with one ray, we're basically getting 5 photons back from that ray, right? Now we cast, I think 8 or 16. We cast, depending on how we tune the parameter and how fast we make the raycaster, we can, if we improve the speed of the raycaster, we could set it up higher, whatever. We're casting some number of rays, and then we're averaging them together, right? So I guess I shouldn't say per ray. This is for all rays, I guess. So if all rays that went out hit the light source from one emission texel, from one texel that we're sending raycast out of for the light probe. So the octahedral map, right, is wrapped around this, right? We've got one texel. We're sending a ton of rays out here, and we're going to hit with some number of them. So coming back, the number of photons that we received at this probe is going to be the emitter's number, which is like the 5.0, divided by something based on how many rays hit, right? So it's times the hits over the casts, right? So there's like an H over C term here. So 5 photons are magical photons, or 5 billion photons, or whatever you want to call this 5. If all the rays hit, that's how much energy would have come in through that texel. If some lower number of that rays hit, we get proportionally less. So we don't really even have to talk about how many actually hit here. We can just say that's what happened. But if we wanted to put a concrete thing on it, let's just say that for some reason all the rays hit. So like everything in this bundle of rays that we sent, they all hit the light source. So we got back the full 5 magic photon quantity, however much that is. 5 handmades of photons, right? So then what we're going to talk about as the buggy part, because I don't see, so I guess what I'd say is I don't see how that can really be all that wrong, because we're setting this number to whatever we want, and that seems fine. Like, it's just, that is just a measure of if every ray hit this light source, you would have that much light energy. And since we're setting this value to whatever we want, I don't see how there can really be much of a bug there. If we were to claim that this value was something else, candelas, watts per steradian, whatever, then we would have to think about whether what we claimed the value was measured in was actually correct. Because it could be if we said that it was, for example, watts per steradian or straight watts or whatever, there might be a thing where you have to divide based on the scale of the light source in order to make the units of that be true, because they might be talking about per surface, they might be normalized to surface area or not normalized surface area, and then this could be wrong. But because we haven't even said what it is, it's just an abstract measure of brightness that we turn up and down, I don't think it can actually be wrong because we haven't made any claims about it. We just claim that when it gets larger, the light gets brighter, and when it gets less, it gets less. So I think this is, again, me just trying to reassure myself that I think that we don't have any problems in that first gather of light from an emitter, because that seems okay. But I don't know. Now let's look at the next bounce, and here's where I think we have problems. So let's suppose that this is the only light source in the scene, and we've only done one bounce. So, meaning we haven't run this for many frames and let the light flow around or anything. So the only light in the entire system, let's say, is there. And now we have more probes. Right? And what we're going to do is we're going to cast, and some of these casts are going to hit, right? Now, some of these, we could easily construct a case where 2 of these probes are on the same line directly into here. And I'm going to make our lives easier so that we know that the amount coming back will be exactly the same, right? To make our lives easier here, I'm going to restrict our discussion to just those 2, because I think that helps us understand part of the problem, right? Or at least why I think this is complicated. So let's suppose we're talking about these two, A and B. Well, we know that no matter what we do, A and B, the light probes A and B, will have to produce the same values, roughly, right? A is a little further away, so it will have some proportion of the light that's flowing into B, right? The ray bundle that comes out here is tighter, so let's say B hits all just the part that would be reflected directly out of here. So B, in this of its texel, would have the full 5.0, but A will have less, right? Because some of the rays will miss. So maybe A goes down to 4.0, like it just misses some. Not that you can have 4.0 in a system where the divisor is 16, but whatever. Well, maybe you could. Anyway, but point being, here is where I think we have the issue, right? Or our understanding of what's happening with the light probes is slightly wrong. So the light probes are just measuring the light flow through that area. And so they, by necessity, have to basically, we have to have the amount of photons that are flowing through the area has to basically be, wait, I missed a step. I missed one step. So this is not quite true of the 5 and the 4, but the point I was trying to illustrate with the 5 and the 4 will still be true, but let's not forget. So in order, these have to hit something. A probe is not something you can hit. So you have to hit like a wall, right? And the wall is nearby to the probe. And so we have a reflectance function of what comes off of the wall, right? And what comes off of the wall here is going to be the total number of photons, right, that hit the wall, which in this case is 5.0. In terms of what comes out in this direction, we have to basically take something that will distribute the 5.0 photons evenly. Meaning 5 came in this way, and if that's the entirety of it, the 5.0 have to go out some proportion, right? We can't send out more than 5, right? We know that most of our services will have some kind of a multiplier on them, and we should go check this just to be sure. But let's suppose there is like the 0.7, or maybe there's even just a 0.5 to make it a little easier on ourselves so we don't have to have multiply by 0.7. Not that it's that hard in this case to do. But let's suppose that it's just like a 0.5. So we know that we have 2.5 of our magical like photon count going out of this surface. And we can distribute it over the hemisphere however we want. Right now, I believe the way that it is being distributed is there's a stage where we take the light probe octahedron and we take the it's basically a specular one, so it's just got like the light, it's got literally like the texel that this went out of is like at 5.0 and everything else is at 0. And we do a blur on that that's based on the cosine fall off, which produces a cosine fall off diffuse version of the light probe. And that, I believe, is the entirety of our like transport equation, right? I believe we made that energy preserving, meaning the total sum of the light in there is the same, the spec map and the diffuse map. Now we can go check that, and in fact we should. We should remember to like check diffuse power. But I believe that we properly did that because we knew when we did that, we're like, we can't add energy to the system. So when we take the spec map and we produce the diffuse map, we have to make sure that it equals the amount of the light that came in has to equal the amount of light that goes out. Otherwise, we're basically adding energy to the system. But we can recheck that. So then we get in here and we say, well, okay, so 2.5 are going out. And, this gets spread along the hemisphere somehow, so we don't know how much it actually is. But whatever it is, let's say 1.0 of it goes out in this direction. B, all of the texels in that direction all hit, so it gets 1.0. Here, some of them don't, so it gets 0.5. Right? Something like that happened. So I believe... So you can see the thing that I'm concerned about here is that we've duplicated how many we've duplicated photons, right? Meaning there are photons now at B and at A. B has all the photons and A has half again, right? It's got 50% of the photons, but the amount of photons we sent out isn't conserved. Now, because these are light probes, I don't know that they should be conserved, because we're talking about how many photons are passing through that point. But it could be that but how do we, do you see what I'm saying? Like, that's what we're measuring. And I just don't quite see where the flaw in that thinking is, because it's like, well, this is talking about how many photons in general are going through this area. But you can see how this would produce a problem potentially, right? Or at least I think this could potentially produce a problem, right? Like, you would assume, therefore, that if this sort of thing can happen, well, if there's further bouncing that happens, like from here or from here, these will basically be bouncing more than the total number of photons, right? I mean, I don't see any way really around that. And yeah, they're going to get clipped down quite a bit, meaning this same process will go again. So, it's only going to send out a subset of them, but it's sending out a subset of them based on a total number that didn't actually occur, right? Right, so suppose this looks like this. Well, that wall in the way wouldn't be good. So maybe this. Suppose that it looks something like this. And we're talking about like the reflectance from here and from here. It's both of these are going to be using, we're going to be computing those bounce equations based on 150% of the light. And even though they'll be knocked down quite a bit, again, you notice we don't immediately get this. It's very slow. It's like a slow creep. So that may be enough to just slowly over time, because the total number of photons being used in the distribution is not conserved, off we go, right? Now, the problem is I don't really know how you would solve this. I mean, obviously people must, because light probes are not weird. But when light probes can collect light from other light probes, which you have to do in a system like this, where it's real time, so it can't just take an infinite amount of time to run, where each light probe just does the bounces itself and tries to hit the light source. How do you fix that? See, this is why we need Don Mitchell here. Where is Don Mitchell? Probably has something better to do this time than this. But I mean, I think I've roughly I'm fairly convinced that that's a problem. That our conceptualization of what the light probes are measuring is fundamentally incompatible with conserving the amount of energy that we actually sample in the system. And I don't know. I don't know how you fix that. Well, let's go back and look at the chat. So, did that make some sense? Thank you. All right, space naming. Maybe we'll set the light bulb down slightly. So, like, I'm just kind of fundamentally confused about how to think about light probes because of that. Nikito97, that's my concern, what you stated. Because I don't feel like I'm very good at light transport, I just haven't worked with it much. I don't want to say that that is definitely true. But that's what, like, based on my thinking about the problem, I don't see how it couldn't be true, what we just said. Like, fundamentally speaking, if you measure flow of photons through a point, there's nothing to stop you from using that flow in multiple places, right? And it's an aspect of the discretization of the problem. If everything were completely continuous, you wouldn't have this problem because nothing could reflect. Like, no two surfaces can reflect the same exact photon if you're simulating all the photons. But when you're simulating photons as bundles, right, you have to use, like, a sampling from the average of, like, some from what direction you're talking about, and you're by definition not going to get an exact occlusion of who's sampling what from where, right? So it seems to me that I don't see how we modify what we're doing. Like, I don't quite get it. Like, I don't quite understand what we're supposed to do about that. We could calculate the amount emitted and the amount received and artificially dampen the emission in the next frame. Yeah, we could, or suck power out of the system, like everything gets that much dimmer, right? Like, you sum the total sampled amount and you reduce it by enough to make sure it stays under the total light level or something. Like, yeah, you could do something like that. I don't know. Yeah, I just don't know. I I feel like this is probably something that it would be good to go read about, right? Like I'm assuming that there's somewhere that someone has written up, maybe when they were first working on the concept of light probes, where they've talked more about light probes that are hanging in space. I don't know. Um, I mean, maybe the problem is that really this is not the right way to think about it because really the problem I'm talking about is a problem everywhere. And so that's not really the problem. The problem is just the discretization. Like, you would have this problem no matter what you did. That's always true, that you're talking about the photons that are flowing through an area or flowing, that are bouncing off a surface. And so really the problem is just that we are discretizing it, so that when we sample, we could sample multiple things that all are measuring the same flow. And because we are, averaging them together into texels that aggregate and are sampled as aggregates, we end up allowing people to gather more light than they should as a result, right? Um, because like if you think about it, yeah, like I think there isn't really a problem with it up until that point. Like up until the point where it goes like, oh, well, I can sample from this light probe and so can this other point. But in reality, those 2 points would not have been able to sample the flux because they're both offset from the line that was that flow, and only one of them would have actually been able to like hit that light source or whatever, but now it appears like two people can, right? And so on. So it may really be more about that discretization than it is about the fact that they are light probes for any particular reason, right? Um, right, because you can imagine taking the light probes out of this entirely and just talking about sample points on like the wall. You have the same problem. If you just count like large angles and you say, well, if there's anything in this angle, then you get all the light, then that would be wrong too. You know what I mean? Um, so we need some way of saying that the light gets distributed between these 2 points. You can't have all the light go to both. You know what I mean? Eventech, we don't do that. We don't propagate light info between light probes. But when you send out a ray to sample what's happening in the environment, you hit something. The only way to know what the inbound lighting at that location is to sample the light probes in the neighboring region, right? So you get information sharing just from that. And there's nothing you can do about it, right? Um, so the only solution to that problem that if you don't do that is you have to do multi-bounce raycasting, which would never be fast enough in real time, right?
I wish I had some better ideas here, but I don't. I mean, so the original paper that we were sort of basing the system on, and to be fair, we didn't really do it exactly, not exactly. Did we save this paper on the hard drive? I don't remember if we did. It was an NVIDIA paper talking about some lighting stuff. I don't actually know if we saved it or not, but that's not gonna do it. But we should be able to go find it probably. I don't know. You'd think we would save it, but we might never have. Docs. It might be one of these. I think this is it. So this is the original paper. And we did, we did pretty similar. I don't think we quite did it exactly the right way or exactly the way they did it, but it's similar. Right? We did a uniform 3D grid. We did octahedral maps, which is what this paper does. And so I wonder if there's something in here that we were missing, because we didn't really look at this part of it. I wonder if they discussed this anywhere. So we don't use screen space occlusion, obviously. They don't really talk much about this part, though. Okay, this is probably mostly what we're care about here. So I don't think this talks very much about that aspect of it. Maybe we should go back to the McGuire paper, which we also have on here, that they reference a lot. Let's just go over and make sure there's nothing we were missing here. Generate and trace n primary rays from each of the m active probes, storing geometry. Yeah, we don't really do this. They're doing so, I guess it's possible that that is helping them avoid this problem if they're actually doing that. So it really doesn't say anything much about it. So like this we're also doing, right? Oh, sorry. I forgot to flip it on. My bad. The bad news is you didn't miss anything. I didn't see anything in here. There is a little bit this so yeah. If you look at what's happening here, they talk a little bit about how they're doing the shading, and they talk about doing cosine lobe distribution, which is what I believe we do as well. So like, if we go, let's open a command prompt. And open the code. So somewhere in here, yeah. So we do this step here, right? Which is where we convert from specular to diffuse. In here. And when we do that, we have it all. We use the values we get from our like pre-computed weight buffer, which is like this nonsense, right? And so if I go look at that, where we build, it's like, yeah. So you can see here we do a cosine lobe, right? Like that's what this inner product here, right? The inner product between two vectors, the incoming and the outgoing vector. Since they're both normal, that's just going to be equal to cosine theta, right? The direction between them. So this is a cosine fall off weighting scheme, and that's really all there is to it, right? And that's it. We do it twice because first we sum up how much it is going to be, and then we write it out by making sure that total, we only ever sum up to the total amount of power, so that the entire thing is normal, right? So that we do that. Right, we do this. So they're talking about this a lot, and it sounds like they're deferring any discussion of it to this, which is not great because this is, I don't know, some kind of book that we don't have, which is less good. We do have the McGuire paper they were talking about, but we don't have this book. And I don't think we can get a book. Can we? We would have to actually order this book, which will take a while. Although, did they just put it online? Hold on. Wait, so it doesn't suggest that the entire thing is available for free, but then on their... Oh, it's the preface. So it's only the this is the... But the preface... This can't be the preface. It's huge. I guess it's just the preface and the bibliography. Well, so we can't really look at that right now, although I could order the book, and then I could try to read it online. So I guess I'm not sure. Let's look at the other paper that we do have, because, hey, maybe it's in there, but I don't know. We could also just order the book and wait, is another option. So let's take a look. Light field probe structure. A scene's continuous light field encodes a spatial angular distribution of radiance for all points and directions in the scene, which is what we want. We build an augmented discrete representation of this distribution, so we require discretization of positions in space and directions. We discretize spatial variation of the light field using a regular grid inside the scene's bounding box. Okay. While this regular structure allows us to simplify our tracing algorithm, nothing prevents us from using spatial samples jittered within each volumetric grid cell during construction and query time. Sure. We might consider that. That's not a bad idea, right? Like inside... When we are sampling from each probe, we could jitter the location of the sample, right? So that's fine. At each discrete sample position, we store a spherical light field probe. Yep. A discrete spherical slice of the light field that corresponds to the local incident radiance distribution at X from surrounding scene geometry and light sources. Yeah. The surface normal at points X double prime closest to X prime in outgoing direction. We don't have any idea what that is. So they're actually storing some geometry. Maybe this is what we're doing wrong. We don't have anything like that. We populate the geometric information of the probes using rasterization and the spherical light field slice radiance distribution. Yeah. Yep. All of our results through the ladder. Okay. First bounce. This contains the emission profiles. Then we repeat the shading to really populate with additional light bounces. That's what we're trying to do. Because the algorithm can use rasterization to compute the probes themselves, we do not require a separate geometric ray tracer. Sure. Section 4 details a ray tracing algorithm that allows us to populate, update, and query physically based light transports. So that's very interesting that they do that. And I wonder if one of the reasons that they do that, because I can't think of any other reason why they do that, I wonder if one of the reasons they do that is specifically because of this problem. Like, they're trying to represent the actual geometry in there, because if you don't represent the geometry, you get this. I don't know. That might not be true, though, so let's keep going. So this also uses an octahedron. And that's fine. All right. So I think I kind of understand what's going on here. It sounds kind of like what they're doing is they store the surface normal of the things that they hit when they store the light probe, so that when they then do the lighting computation, they can use that surface normal to determine how much light would have come from the target surface in relative to the surface that they're illuminating. And again, that might be part of how they avoid this problem, because they actually are simulating the light transport more exactly, right? Generally speaking, every physics renderer, atop a ray tracer, where arrays are used to resolve visibility and to sample radiometric quantities, sure. Concretely, array is a half line with points. Yeah, sure. Our light field ray tracer first selects a probe, then invokes a single probe ray intersection routine to march across the geometry defined by that probe. If the single probe routine is unable to accurately determine a hit or miss event, then the algorithm advances to the next candidate probe and reapplies the single probe routine. As such, the single probe routine returns one of three possible results: a definitive hit, a definitive miss, or an unresolvable exit code. The latter occurs when the ray passes into a 3D region that is occluded from the probe's center of projection. In other words, when a probe knows that it does not have the required visibility information at a region of space. Okay. An intersection for a ray that passes through that region cannot be reliably computed using only information from the one probe. Note, however, that by increasing the density of light probes stored in the scene, we are very quickly able to guarantee accurate roll space. Okay, sure. The light field ray tracer selects a probe, traces within that single probe, then repeats the process until infinite. Okay. A line segment in R3 maps to a polyline with at most 4 segments in R2. After spherical octahedral project. Okay. Each polyline segment lies on a separate octahedral face, and the 2D coordinates of the segment endpoints are the 2D projections of the intersections of the 3D line with the 3 principal axis line planes that pass through the probe center. These define 8 quadrants that correspond to the octahedral faces after projection. Wait, so they're actually talking about tracing the ray on an octahedral map. What? Okay, that's very different than what we're doing. And very different to the other paper. Okay, so they basically are talking about walking the actual packing. I'm so confused, but okay. So most of this won't really apply, but let's see what they do when they actually get. Do they talk about what they actually do when they get a hit? We now describe 3 global illumination algorithms, the latter 2 of which are practical: a brute force impedance sampling Monte Carlo renderer, and more efficient. A more efficient extension that reduces the number of ray samples required by post-filtering, an extremely fast but biased solution that pre-filters then burst reflection and only traces rays for glossy reflection, which is also which sounds more like ours, and I wonder if the biased part is kind of the same problem we have, which is that it's brighter, it feeds back over time. But let's see. So I'm not really sure. I'm still not really sure I see much going on here. So I want to ask a few questions. I think we left this, yeah. So you can see the light leaking that we're talking about, or the light sort of slow bleeding to everything in the scene that we were talking about here. I'm curious to know if we were to, when we, like, let's say this light is only ever at 1.0. So, it doesn't have any higher value it can reach. Does it still contaminate, or is, how sensitive is this to the number, right? Um, I don't know, and I wanna kind of know what's up here. We should I wish we had decided to work on the light occlusion problem, which you can see here, because that's a lot easier for us to fix. But unfortunately, that's not the problem we chose to work on today. We chose to work on the harder one. This is when you occlude a probe, right? When something moves over a probe, we don't handle it right now. We just write black onto it so we can see that it's wrong. But so it doesn't seem like we really get that light contamination. You know, I just don't understand. If we set the light value for something up to a certain amount, it starts to have that contamination effect. But maybe that's just it slowly spreading its light around and producing a correct value. I don't know, right? And like if you had exposure in here, then this would just adjust. So I really just I this is perplexing. I feel like we need someone who's an expert in this, right? But you can see how that you can see that anything over 1 has this slow effect where you can see it go, and anything that's not somehow oddly doesn't, which is strange because it shouldn't it? I mean, why wouldn't it? I'm not sure I understand why it wouldn't do that, right? Because if what I was saying was true, like why doesn't it happen here? It feels like we've got some, there's just some fundamental. Yeah, Dr. Zool, that's exactly kind of what's making me concerned, right? Because if there really shouldn't be that shouldn't be the 1.1 times 1.1 is larger than the original kind of a thing should not be a factor. So I'm wondering if maybe we really do just have a bug somewhere that is actually having that exact feedback problem. Although I suppose... yeah. We should probably go fix the occlusion bug. I wonder if we should just do that first so we don't have to keep looking at the weird like blackout problem, but... So that's just a real stump ore. We know we're doing cosine lobe, and we know that it ends up summing, unless we screwed that up. We know that it ends up summing to the correct value. Of course, we are doing, bilinear filtering, but I don't think that would have much of an effect, right? This is the filtering code right here. What? So I will say this is a bit odd. So we have the occlusion. So that occlusion D value, what that is it's saying that, we're not gonna want to sample from light probes that are in the wrong direction. So the prox 1 over is just letting us know, like, we want our light sample to properly, like, average across only the samples that we're actually taking, right? Which seems fine. You know, I'm not too upset about that. I don't know. This is a real puzzler. I really just don't quite know. What, by the way, are our surface colors? Like, in terms of our, occluders that we're loading in here, like, how much light do they generally absorb? Would be my other question, right? Like, when we are actually adding occluders, what is the general reflectance that we would expect to see? So, it's this here. And here are all the places we add them. So color.rgb. So, a .888, it takes out 20% of the light. In either case. actually know if that, I guess that's using the same color here. And then in the apron, it's darker. It's half. So we know that there's a fair, like, there's quite a bit of dampening. It's taking out 20% of the light on every bounce in that case, and it's taking out half the light in this case, right? So is that actually happening here? I guess I don't know. It should be, because, yeah, I'm pretty sure that in here we are definitely using the ref hit color, right? Like, that's definitely happening. I don't know how that happened. So you can see here where we take the probe normal and we have the hit ref color. And when we take the probe sample here, at the very least, we are multiplying by the hit ref color, right? So I don't know. I don't really see. I really don't see the error. I suppose that if it's just straight feedback, right, then we should also be able to predict that since most things in the scene are 0.8, you would expect there to be no feedback if we set the light level to just enough, right? Like, so if you assume that we want to take, 0.8 times x equals 1.0, right? So we're just saying, look, if we take 1.0 and divide by 0.8, we get 1.25, which would be presumably like roughly the steady state. So if I set this light up to 1.25, we would probably expect that because every bounce will take out at least 80%, that this would not feed back, right? And it doesn't appear to. But if we go above that to say even just slightly above that, maybe to 1.3, we would now expect it to feed back on the interior, but not on the exterior where things were set to 0.5. I don't know if that will actually happen. Maybe there's more getting taken out of the system. This would be very slow, but in theory would eventually feed back, right? Doesn't really look like it, though. Again, I'm just trying to gather clues to what's happening here. We'll try a little bit more, 1.5. I don't know. So I can't really construct a valid argument for why we have to set the number to something particular to feedback either, right? Again, which is kind of perplexing. Unless I'm just like missing something. That looks like it might be feeding back a little bit. Yeah, you can see that is feeding back. Very slowly. It takes a very long time. Is it possible that the color dampening hits some negative values and adds to the lighting instead? The color dampening. Oh, you mean like these? Well, I don't think so, because they're all clamped. I think. Like, these are both clamped. I guess I don't know. I'm not sure to what extent those are clamped. One thing I do think we probably want to do eventually is rewrite this to be ray bundle based now that we are always shooting ray bundles, but yeah, we did always have this problem, I believe. It doesn't, now that we are much faster, it spreads much quicker, because you have to remember, like, it's very hard for this feedback to happen if the total, like, contamination number, like the contamination speed is capped. So, for example, in here, when we used to say, like, this was going to be much lower, so let's say this was 1 out of 60, so there was a 1 second of lag, it takes a lot longer for contamination to occur. So, because the light is so laggy, you won't see this contamination unless you hold a particular location for a very long time, right? And that's just because it takes so freaking long. We can probably set this up. So, 2.0 was fairly fast contamination before. I believe at 6. It's simply not going to be very fast when it's got that dampening on it. It takes a really long time, right? So before, when the lighting was really slow, you wouldn't have this problem. Later, we upped it so it's 6 times faster now. You get a tremendously faster contamination, right? So something that was not visible is, like, very visible at 6 times speed. And again, that's just because now we can just run it so much faster. So I don't think we actually had this problem happening that often before, and the reason for that was the lighting was too slow, right? Now that the lighting is fast, any feedback effects, we will always actually see them, whereas before they were kind of, like, hidden from us, right? So, getting better in a way made us get worse, right? It made it harder for us to, to get away with things like that. So I don't have any idea how to progress here. I feel like what we need here is education. And we need like we need to have a more solid idea about how we're computing these equations so that we have an argument for why they wouldn't just feed back. You know? I also would like to know how much feedback there is in sort of the broader sense of the term. Like if we had like what would this look like if we just had a exposure curve on here? And like maybe that's an easy thing to add. I don't really know what kind of exposure curve we want to put on here, because that's kind of a tough call separately. But, you know, at the moment, we don't apply any exposure curve at all. And so if we were to go into, like, how the lighting is sampled here, right, we do one of these, like, surface reflect things. I guess there's a fogging factor in here still for no real reason. We don't use that anymore. But we don't really apply. There's, like, a clamp in here, right? But we don't actually apply any kind of I don't know why this is written out manually either. We don't apply any kind of curve to it, right? So we could apply an exposure curve, like a really simple one, like a brain dead one, to see what happens. Like simple exposure curve. Oh, no. Shader simple exposure curve. Yeah, I mean, sure. I like Learn OpenGL. So that's Reinhard tone mapping would be fine. And that's just the color of the color plus one. It's not good, but that would be fine. That would be fine. I'm fine with that. Let's just see what happens, right? First of all, is there a reason why this was written as 3 of these? Like, can we not just do this? Does that not work? Because I don't know why that wouldn't work. Yeah, so that seems fine. So I'm just curious. So if we were to clamp this as it over itself plus 1, which again is like just brain dead, you know, brain dead tone mapping. What does that do? I'm just curious. It didn't like how I wrote that. Well, you know what? When you don't close your parentheses, that's a valid thing to complain about. I agree. Shader compiler. So here's a tone mapped version of the output, just so we can kind of see, but it still looks completely feedback. It's still totally feedback, right? To me, like that's not producing any actual light. Like it's totally not actually producing lighting there. It's totally feeding back. So I really think this is just wrong. Like I really think we just have something wrong-headed about the way that we're doing it. It always floods the scene with light, and it doesn't have anything to do with what the actual overall values are that you pick. It's just wrong. Yes, beginner questions are okay, by the way. Although we don't always take questions while we're actually working. Um, but beginner questions are definitely okay. I answer beginner questions all the time. So we really do have some, yeah, and I just don't feel like I have the necessary, like, I haven't figured out how to think through this problem properly. So, like, we're just not, oh, I forgot those skull guys can go anywhere they wanted to. I'm going to run away from that. So we have issues here that we need to address that have to do with that overbrighting that's happening there. And there are a problem with thinking in terms of, like, how we avoid using the same lighting in multiple places such that it feeds back on itself. And I literally just don't have any idea what it is that we're doing differently as far as sampling the light probes go. It could still be a bug, but based on the light board, I'm just not sure it actually is a bug. I mean, it's a bug for sure, but it's not a bug of the form like we forgot a minus sign, right? I'm still concerned that it's a bug, meaning that the strategy is busted. We're missing something that's supposed to happen here that we're not doing. The other thing I would say is maybe, is it possible that when we thought we turned off probe to probe transmission, that somehow we didn't actually turn it off? Like maybe that is what's happening, and so when we tested to see does it still happen with that, we turned it off, and then it turns out we didn't actually turn it off. I don't know. That's possible. I don't think that's likely, but you know, it's worth checking. So in here, right, we have a thing we do where we say if we hit the apron or walked too far without finding an intersection. So like we don't hit anything. We have a thing here where we can turn on like zeroing out the hit ref color and the hit emission, so that like basically it just won't or the argument is it won't be able to sample anything if it doesn't hit a surface, right? And I think we proved that the feedback happens anyway, right? You can see it still happening. So I'm pretty sure that that has nothing to do with it. I mean, similarly, the grid walk iteration part of things, we can just turn off, right? We can just say, you know, equals 8, and it will never equal 8 because we're not adding anything to it. So now we know this will only happen at the apron. All rays will be cast as far as they need to get cast, right? And we still get exactly the same problem. So I'm pretty sure that probe to probe contributions just aren't an issue, actually. So probe to probe, and you know, honestly, it seems like we don't really care about that anyway. It looks like we could just not have the grid walk iteration terminator as well. Like, I don't know, this part seems kind of irrelevant. So it's pretty rough. It's pretty rough. Valbus, yeah. Well, I don't know that I would call them sampling errors, but like I was saying before, the discretization of the problem seems like it could be part of it, because you can sort of get the same light probe's light, the same light flow reflected off multiple surfaces, potentially erroneously. Now, You know, when we sample, and you know, the like we don't keep the normals, which they do, so we're not using the like normal to normal fall off either. Yeah, I don't know. Oh, there was the copy paste the transfer PPS accum line. Can we peek there again? Sure, yeah, of course. Is this which one? So there's this one. But that may not be the one you're talking about. Can you be more specific about which one you want to see? I can scroll to it. But I don't know which one. You're talking about like when it adds, or like this one here. 0 as last args. But I think that's correct. Right? This we probably want to rewrite this in terms of ray bundles now that we're doing things fairly differently. So, you know, this stuff is kind of inefficient. As you can see why some of these, look with some of these to-dos and stuff. But the way this was doing it before, right, is the shuffler was picking out, you know, one of the reasons I think now we could switch it to that is because we've simplified things so much. I think we could switch this to doing ray bundles, and they all cast out the same. Before we were casting out 1 ray per texel, now we're casting out like at least 8. So going as a ray bundle would make a tremendous amount of sense, probably. I mean, in some cases it wouldn't be fantastic, maybe, but I think it would be plausible that we could do that. But the point is, the way the shuffler stuff worked, it's been a long time, but just my recollection of it is the shuffler just picks out which one was the actual best hit. Right? So when you pick out which one was the actual best hit, I believe it shuffles the value that is the correct value. It shuffles that value to the front. So I believe this is supposed to be 0 everywhere. Right? I don't think that's copy pasta, I guess is what I was saying. I think that's just correct. But, you know, I certainly could be wrong about that, but I don't think that's actually wrong. Does that make sense? But I'll go you one further and just say, like, let's suppose that was wrong. Then it's still probably fine, because the RG and the B for our surfaces right now are the same. We don't actually have any color in the reflectance. You know, we just don't right now. So, you know. The second argument is just saying which lane you wanted to pick out. So basically, like, if you were trying to extract the first one, here, I'll show you. If you're trying to extract the first one, yeah, I mean, well, you can see it here, right? You pass a 0 to extract the first one, 1 to do the second, 2 to do the third, 3 to do the fourth, right? And this is easier. You don't have to do it this way if you're not on SSE2. There's faster ways of doing it on more modern, like on AVX or whatever. You've got like extract calls. This is very inefficient. Like, I do think we could get Now, at this point, we could probably get a pretty significant speed upgrade by rewriting this code to be wide on raise, because then this entire code actually unwinds into just its scalar equivalent, and it does 4 arrays at the same time, right? And that would probably be dramatically faster. We would slow down a little in the grid walk because the grid walk would get slower. The reason for that being that rays that early terminate keep marching. So we don't, even that might not get that much slower because you're coherently pulling potentially this from the same locations, which might lead to better cache behavior as well. I'm not really sold that may not really be true, but so probably this wants to get rewritten, but it probably doesn't need to be written right now because that's just largely speed. It's not going to change the bug. You still have the exact same bug after we were done rewriting it, so I feel like we can just save that for but it would clean up this routine a lot and be less, and it probably would run faster as well. So we probably do want to do that at some point. That would be my guess. So we still would have to, at the very end, we'd have to broadcast out. We'd flatten down. It's not really broadcast. We'd flatten down and sum, because we probably don't want to cast in the same wide as we're doing our summations here. I mean, maybe we do, because it is RG and B. It might be that we could even leave it and then shuffle them. I don't know. I don't want to talk about that right now because that's all performance stuff. It's a lot simpler than the bug where it's meticulous work, but it's easy to do. So we can do that at any time. It's not a big deal. Just a little bit of elbow grease. So really, what I'd rather focus on right now is the bug, right? This is a definite bug, and it's just a lack of understanding. Like, I don't actually think what we're seeing is wrong based on how we've defined what's happening. So it's like, I feel like it's our actual definition that needs to be changed. The problem is I don't quite see how you change it. And so that is the real puzzler. Maybe we go back to the light board and just see if we can figure something out. I don't know. Maybe I go get some more fried pork skins, and I eat those, and I drown my sorrows in pork skins. But like I said, I mean, this is really just a hole in my light transport knowledge. I'm just not comfortable working with light because I've never really spent the time to do it. If I had done a lot more ray tracing work in my life, this would not, I'm sure we could work through this problem very quickly, right? So the main problem is just my, relative infamiliarity with the right ways to think about light values. So there's probably just a very simple thing that we're missing when we're doing the sampling. And I just don't know exactly what it is. Mindmark, the thing that what the light probe paper was talking about with respect to storing normals is that if you look at what we're actually storing, and we don't have unfortunately a very good way of visualizing it, but I can turn on in debug draw. So here. So if I draw the actual what we're sampling, the octahedral values that we store at each light probe, this is just a visual representation of them. And you can see, right, each one of those directions, I'm just showing the light and that's flowing along those lines. And you can kind of see that, until the light contamination problem, it's fairly sane. You can see our other bug here. You can see why the reason that is black, there's no light flowing in there. is because we currently don't handle when a light source is occlude. So like a light source surrounds it. So there's a light source right here that's basically like enclosing it, right? So that's the other bug, but that's a much simpler bug because that's more just us deciding how we're going to handle that. That it's not like a hole in our knowledge, right? Let me turn off the light contamination for 1 second so I can finish explaining what I was about to explain as well. So, oops, no, stop. There we go. So if we turn this back down to a non-contaminating value like 1.0, and then I run it again, and we show those values again. So what the papers actually do is, in addition to each one of these normals, they also store in that direction the last hit that they had. Well, not the last hit, the average of the hits. They store what the normal was that they hit. So, like, for example, in addition to that, we would also store, well, and in fact, I can even sort of show you, I don't remember if we left this on or not, but doesn't look like we did because I'm not seeing it anywhere. So maybe we turned off the debugging. Yeah, I don't... Normally we would see the little debugger on here, but I don't actually see any evidence of the little array debugger. Why is that? Oh, you know why? Grid raycast debugging is probably just set to 0. Let's turn that back on. Okay. So in the paper, I should now be able to show you what I was talking about. Oh, that's interesting. So do we not... Oh, right, because it's white noise now, so it's kind of just random. Yeah, all right, cool. We would probably have to put a pause on that so that we could debug it if we needed to debug it further, but I forgot we changed to white noise so that it won't be a stable array. It will be kind of an arbitrary direction. So what you can see here, right, is one of the samples that's getting taken out of this part of the octahedral map that sums into, if we look, kind of straight down the barrel here, you can see it's that there's going to be like a texel there that's being represented. And these are some of the sample arrays that are getting cast, and it's white noise, so it varies per frame. You can see the darker brown line there is the normal that we hit, like the surface normal at the point that we hit. Now, we do use that surface normal to, when we compute how much light we will record as coming back into the light probe here, we do actually have that value used in the sampling, but we don't remember it. So later, when somebody samples from this light probe, they don't have any information about what the actual surface normal was in the direction that they were going. I think what the paper does is the paper assumes that when you're going to sample the light probe, they check to see if the surface normal was mutually occlusive with the surface normal that you're sampling from, right? So if the direction you're sampling from couldn't possibly have hit that surface normal, then it doesn't use it, right? That's my guess anyway. So that they basically store that normal so they can have more accurate, which, does that, I don't know. So the other thing I would say is, like, maybe part of our problem, is part of our problem here just that the numbers in this system have to all be less than 1 always, because of some aspect of the system that I don't totally understand, which means that actually we don't really have a bug. We just need to change all of our light values to be lower and then the tone mapping curve to be higher, and then it's just, we call it a day. Because one thing is like, why aren't these lights feeding back? Right? And I have no idea. So if, for example, and I'm just going to, like, let's just go down that route slightly. So let's suppose that we, I don't actually need this to be on. Let's suppose that we did that. So when we've it all, if we were to turn off the lighting entirely, and so now, the glove is the only light in the scene, and you can see it, and we have our bug where it occludes the light source, right? You can kind of see it literally doing that, right? But other than that, it looks correct, and it doesn't do any light contamination. But maybe we want that to be pretty bright, right? And so what we would want to have here is our exposure curve would treat that lighting as pretty bright lighting or something, right? I don't know. I mean, this is kind of, I'm definitely winging it here, so I'm not trying to say anything as if I know what I'm talking about when it comes to this kind of stuff. But so let's suppose like that was supposed to be pretty bright, and so what we want to do is we want this to be mapped to a curve where you assume that this light is quite a bit brighter than it is. So it's like, like 1 is like 10 times the brightness or something, right? Like it's just way brighter lighting than before. I don't know what this is going to do, but I'm just throwing that out there, right? So like that is like the glove is like a very bright light now, because 1.0 is extremely bright. Maybe it's even brighter than that. Maybe it's like it's 100, right? So like 1.0 is like a super freaking bright light, the brightest light you've ever seen in your lifetime. It's so bright that we can't even handle how bright it is, right? Well, we don't get the feedback problem, but we get the same output, right? You see why I'm confused about this, right? Like, it doesn't make good intuitive sense, but you can see kind of where I'm going with it. All right, and now let's suppose we add back in our standard lighting, which is now going to be way too bright for us. We don't want it to be so bright. So we're going to have to bring those lamp lights down quite a bit. They're at 10, which is much too high, right? So I don't know what they should be. Like, let's say 0.1 or something. I'm not sure. Something like this. We now get the same effect. Like, you can see why I'm confused, right? We get the same effect that we wanted, a very bright glove, so bright that it's brighter than we even would want, right? And I can remove those. Where the heck is my debug draw octahedral? There we go. It's so bright that we probably wouldn't even want it to be that bright until we actually have some kind of a tone mapping going on, right? But we have the exact same thing we had before, but now we don't get light contamination. Like, it's massively bright right there, but it simply doesn't cause that problem. Right? So, something about something about the fact that the numbers have to be 0 to 1 is like there's something fundamental about the fact that the numbers have to be 0 to 1 that we don't frickin' understand, right? And so, and I mean, the good news is that means we don't really have a bug in the code. The bad news is it means we have a bug in our brain. Right? The bug is in the brain. The bug is coming from inside the brain. But so yeah, I mean, we're kind of fine at that point. No worries. I mean, the glove is now too bright, so we would want to tone the glove down as well, obviously. But you can see what I mean. Like, there's just a fundamental thing about keeping the values between 0 and 1 for lighting. I obviously just don't understand that. Like I obviously wasn't thinking there would be a difference between those things, but there's definitely a difference between those two things. So I'm very confused, right? I just don't quite understand why. And so something like this basically looks correct, right? Like, this looks like a game that you would play and that you would buy on Steam or whatever. And we didn't change anything. We just remapped our values to be in the 0 to 1 range and applied boosting after the fact. Now, of course, we have to reduce the exterior lights as well. I suppose I should have done that as well, because we have like a moon thing that we like add. When we generate the apron, there's like a moon light thing here that we did, and that's like going to be way too bright now, so I don't know what that should be, like 0.025 or something, I guess. I don't know. Still actually quite bright, so I mean, maybe just 0.01 for exterior. And you know, that's maybe about right, but it really should be pretty dim out there, because there's, you know, I don't know. But that's the moonlight outside that we were adding, which is supposed to be quite dim, right, as you can see. And that's fine. But yeah, I mean, we just totally got the effect we wanted, and literally all we did was like renormalize the values. So, all right, so there's something broken in our brain there. We should probably figure out what it is. Also, our square like light problem got a lot better as well, as part of that. So obviously, like, you know, tone mapping needs to be high on the list of things we're going to do here, because getting that right does seem like it's probably something we want to do. But either or, yeah, whatever. Let's let that one sit for a little bit. I don't know what time it is right now. It's 2:00. Yeah, gorgeous light that we don't understand is a very good way to describe it. To be fair, we understand a lot of it. There's some. So let me phrase it this way. One of the values in our system is clearly either the lighting or something closely related to the lighting I'm just going to say the problem is that some portion of the system is inherently working as a percentage that we did not anticipate to be working as a percentage, right? We've got a unitless value in our system somewhere that we didn't think was a percentage, but has to be a percentage. And if that percentage is 110%, then it just grows over time. And if that value is 90%, it does not, right? So we fundamentally have a unitless value in our system somewhere that's screwed up, right? Okay. But we still have another problem, the darkening. We know what that is, and we have to kind of think about what we're going to do to solve that problem. There's a number of ways we can solve that problem. We know exactly where it is and what it comes from. There's a way we can mute that problem, like make that problem be less bad, but we want to actually fix it. So where does that come from? Let's turn on the debug drawing again. I explained it before, but let's explain it again because we weren't working on it before and now we are. So if I debug draw the octahedral values again, so you can actually see where all the lighting is, you know, and I take it one step further and I draw the spatial grid as well. So if I go into debug draw spatial grid, there's just going to be a lot of visual noise here. I apologize for that. We don't have that great a debug viz in the lighting system, so you know, if we take a look at this, what you can see is like there's a big kind of fat light that we just added here. You know, we haven't done much work on world generation, so we just threw in a light. And the problem is that light that you can sort of see here, it's this, you know, this interior set. Like these are ceiling tiles here, right, which we don't draw because we want to be able to just see through them. So these are ceiling tiles, and then here this is the light source, right? That right there is the light source. And you know what I could do too? I could try doing a thing where I draw those. Have you ever tried this? Debug, draw spatial grid. Have you ever tried just like using the color of the actual leaf node? Because we must have to store that because we use it, right? So you know, ref color here, that, you know, that is what that is. And our is emission value, we could, you know, we could sort of put those two together, and try to make this actually show more of what the actual system is. So I could do something like, instead of this being a checkerboard here, I could put a thing in here where we set the color based on that. So, you know, get component of this leaf ref color, and we take E out of that. That gives us the color value to draw, and we would need to use the emission as well. But what's your complaint? Operator type of really? Because that's a V4. That's why. Can we do this? I think we added that. Yep, we did add that. So if I draw the colors of things, you might be able to see them a little bit better. I don't know if you actually will or not. So let's try to make this work. I don't know why those are all white, though. That doesn't seem right. Well, I guess they would kind of all be white. That's sort of true. I need to account for the emission here. So if I account for the emission, let's give that a shot. That would show us where our light sources are pretty cleanly, I think. We don't have a get component for one of these. Oh, you know why? Because you can literally just type that, probably. Yeah. So here you can see reflectors versus light sources. So black is reflectors, white is light sources. Or rather, the light sources are colored based on what light they emit. So, you know, cyan because it's a cyan light source, white because it's a white light source. So in the world, what happens is if a sample point starts out inside of anything, like geometry, whether that geometry is a light source or not, it doesn't take any samples, right? And instead, what should probably happen is it should just, that sample should not bother casting a ray. It should just write the value back, right? And so It's a really tough call. I don't know what we want to do here. There's a lot of ways we could tackle this problem, and I'm just not sure which one makes the most sense for us. Currently, the reason that we just stop is because we do a pre-check to see whether or not we're inside anything, right? So in here, once we go to the full cast, this code right here does a pre-check on every place we're going to cast from, and the first thing that it does is it says, well, if you're entirely inside one of the piece of geometry, right now what we do is we just spam black into there, right? And we could do all sorts of things. We could do nothing, right? Like we could literally just leave it alone. And that would avoid the flicker problem. So like if we just left it alone, that would mean that, for example, we don't get the darkening as the glove moves around, right? So that would, quote unquote, solve that, that part of the problem. But you'll notice we do have sort of, we still do have a bug with the lighting, right? Which is that we get contributions from the glove when it is like cleanly in between two of these, but as it like occludes them, we don't get much, right? So we lose light that should be showing up, reflecting on the floor is not going to be. So it feels like what we'd want to do here is we'd want to actually, treat those samples more properly. Now, the slowest way to do this would be to actually run this check on every sample that we take and jitter the sample location out to the radius of the voxel. So we would just sample randomly in the voxel and raycast randomly in the voxel, right? And we would sum up the number of these that were inside. We would add that much light to the actual outgoing spectexels at that point, right? And I just kind of feel like that's going to be too noisy or too slow. I don't know. But I don't see a lot of ways around that, because as lights move over, we need that to be reflected. So I don't know that there's a lot of ways around that. I mean, we could do something where we add light into the system here with a forward pass. And that might be better, actually. So let's ask a separate question. So let's suppose, what happens if we just turn this entire branch off? So now we let the things cast from inside. What does our caster do when you're casting from inside? What happens? Like, does it just hit the thing and that's fine? Because if so, it's kind of cheese. But if that's cheese, if that's the cheese that we have in our lives, like what happens if I try to, I don't know, I might not be able to really get this positioned in a way that it quite occludes exactly. But these light sources all seem just fine, right? It's not correct because they're casting out and actually having to hit the thing. But maybe for like the purposes of real time where we don't really want to add more work, maybe that's just fine. Like maybe we just cheese that out and we just say, look, it's cheese time in the cheese corral and everyone should unbox the government cheese, So I'm willing to do that for now. I would document this for sure because, it's totally wrong. But I just don't want to slow things down too much because, yeah, I mean, I think that's... I think it could be very costly to do something better there, and so if we can do something wrong but that works okay, I think that's probably fine. So I'm just going to say... Although, yeah, wait. Now that I think about it, though, that's not quite true. Because you know what else will happen? We'll get light leaking through walls, right? In fact, we probably already had that happen. We just didn't notice because I wasn't paying attention to it. Right? So you see how, like, now the walls are all, like, kind of lit uniformly? The reason for that is that in there, they're actually able to collect light. I would, however, ask why, because I thought we're sort of... I thought we were saying that you couldn't collect from a normal that couldn't have reflected back to you. So actually, that may mean that we're missing a normal... No. You know what? Probably we just don't test against back faces. So it probably just can soar out through there. Okay. So, yeah, we would at the very least have to check to see whether the thing is an emitter or not, right? We could let you do emitter casting and force you not to do other kinds of casting. So let's see what we think of that. Again, still cheese, just trying a different type of cheese, more like maybe like a barnyard cheddar, as opposed to something like, a Danish Havarti or something like that. So let's take a look at what we would do if we were doing this inside mask here where we did inbounds everywhere. If we basically said you can't do occluders, we would have... I'm sorry, you can't do emitters. We could do is emitter equals leaf is emission, right? And then we would say that value, if it's greater than 0, yeah, we would say, and not emitter, we would say something like not emitter equals is emitter greater than 0, right? And knotted, which we may have an operator for, I don't actually know. That is not the right variable declaration. I might as well call this by the same name as it was. So we don't have Mr. Noddington there, unfortunately, which is a bummer. Let's find out why. Whose idea was it to not have that? Or did we just call it something else? Like, we obviously had an and operator. Like, you can see we've got all the rest of them. Did we just cheese out and not ever put in? Oh, you know why? Because it's not really not. Like, we're going to be doing the entire flip, so it's really like a, it's a tilde, but we didn't implement that one either, so it's hardly an explanation. So that seems fine. So actually we can just do an and not, and we don't have to really, like, even do the not of it anyway. Right? So I think that would produce the right lane-based equation for emitters don't stop you, but other things do, right? So it's inbounds and not an emitter and not an emitter. We should now have both of those things, maybe. And again, slightly cheesy, but I think that would probably be fine. So I don't know. I mean, it's not as good because you want the, and maybe we could combine these two, right? We could combine it with a forward flood fill. So we look at light surfaces and we would write the light surfaces into the light probes, like at those locations. All right. I mean, fine. So yeah, we could have changed this to just equals, right? Another way to write this, if someone was asking about this in the chat, we could write it the other way. Right? You could do that. And that's just saying if you don't emit light, then you're a positive, you're a positive includer. Same. Right? So maybe that's just an easier way to read that anyway. But you can still see the problem. So like if you take a look at what happens in here, like if I punch out to here, you can see that this should be having a bunch of actual light in it. It's kind of hard for me to hold down enough keys at the same time here. But you can see like what this light probe is showing right now. I push out the light and it's actually enclosing it, and yet you don't see much contribution, right? The reason for that is it can't hit this thing, right? It's only able to pick it up indirectly. And so I feel like we might also want it to write the lighting into the probes that it is, into the grid locations where the light overlaps. So like a forward pass that writes lights into things they overlap. I'm wondering if maybe that isn't just a good idea in general. Like, suppose I can turn off the spatial partition. The debug draw spatial grid thing doesn't need to be on there anymore, obviously. I might leave the octahedral values on while we're looking at this particular problem. But, so like, these directions are also now BS, by the way, because we're still using the, like, we're using the sphere, right? We're using the sampling sphere to draw them, but they're casting white noise, so it's total nonsense that we're drawing, right? Like, this is drawing, oh wait, no, it's using the voxel, so that's fine. It's not. I take it back. That's nonsense. I was saying it's using the voxel, so it's just showing the direction of the voxel. That's totally fine. So yeah, gosh, the question is just if I was to do that. So suppose I was to write the light values into the grid as a prepass. So when we're putting them in the spatial partition, anytime we see something with a emissive value, we rasterize that into the light probes. What does that do for us? Does that do... How do we... Because I don't know... The total size of Handmade Hero is... sorry, what does the total size mean? Do you mean like lines of code? Or something else? Because, yeah, I think we could get this a little better by rasterizing the lights as a prepass. I like the fact that with the collision detector turned off, we can punch through and make a light outside the wall. Because you can kind of see that you get sort of a blinking effect too. Like, right, so it would be worth it in the dark. I think we would get much better results, right, if we did this, because you wouldn't get so much variance in the brightness as this kind of bobs around relative to light probes. You get a much more constant value, which is, I think, what we would want there. So I do think it would be a good idea. Oh, how big is the binary? Oh gosh, I don't know, because we don't really build a small version of the binary at the moment, so it's probably quite large, actually. So yeah, it's it's around a megabyte. We don't build a small binary at the moment, so it's around a megabyte. It still includes the C runtime library, even though we only call like one thing from it, so that also bloats us out, unfortunately. So it's fairly large for no real reason, but about a megabyte. Oh yeah, without assets, I mean we have like tons of like assets are large in this game. They're fairly high res and 2D bitmaps, so that's no way that's fitting in a megabyte unless you do some demo scene coding, right? which you could totally do and try to get it down, but right, we don't do any of that. So yeah, but yeah, it's about a megabyte executable. It could be much smaller than that. I think that's kind of like very wasteful. Size-wise, we could be a lot smaller than that, but at the moment we're just not. So I think, yeah, I guess I would say I think we should maybe try a light rasterization pre-pass there, because when we go through them, we know when we hit light sources because we have to insert them into the spatial partition anyway. And we know that they're not going to be sampled correctly because when we sample to them, we don't know what to do when we're inside them. We're not sure how we would really gather that. And it seems like it'd be faster to do that forward than it would be to do that backward. So what would that look like? It would basically be like for each light source, we step through the voxels and see how much voxel overlap there is, and then we add like that much of that light source in. But what direction do we add it in? Right? What direction? You know? I ask you. It's 2:30. Do we try to do something with that today? Yeah, because friends. Yes, let's just add it to the left. The lights in Handmade Hero, lights go to the left. That's it. That's the limitation. It is a deliberate artistic choice. In Handmade Hero, that lights go leftward. You don't. If you wanted a light that went right, you got to go use the Unreal Engine. That's just the rule. Okay? There are other engines available. If you wanted light sources that shine rightward, then that is why, you go use Unreal Engine or something, because they added support in Unreal 5 for lights that shine to the right. Okay? We're just not adding those in Handmade Hero. Lights all go to the left. That's just an artistic choice that we made. And we just think that lights that go left are inherently more interesting, and visually they're more visually interesting than lights that go right. And I think that's what differentiates indie games from these big AAA games, right? So that's what you get. No, in all seriousness, what I mean to say is that if you look at how a light is going to be distributed, so for example, we want a light, we've got a light centered on the glove, and as I move it around, it moves. But what we want to do is make sure that it actually gets more representation in the light probes that it, is actually overlapping, which at the moment it really doesn't get. And so in order to do that, what we want to do is say, well, okay, if we were to add light based on the volume of the light source and how much it overlaps each of the constituents here, the light probes that are likely to see it, what I assume we would want to do is we would want to have the light, you would want to add light proportional to how much of the light volume overlaps the voxel volume for the probe. And if it overlapped the entire thing, you just add it in all directions. But what if it only overlaps this one half? You would expect it to not add light to the other side, right? And that really is the thing that I'm not sure what I would do. Is what I'm saying logical? like am I correct in saying you would expect it not to add to the other side, or is that actually totally false what I'm saying? And you wouldn't. So it's the light that passes through the area. Light should not be passing through the other direction, right? Because the light itself is on the other side of the volume, so you would only expect it to be kind of going one way away from it. You wouldn't expect it to be going the other direction. Although you wouldn't probably care that much if you were, right? So maybe we do something like this. Maybe we say that we take the closest point on the light source volume to the light probe center, which will actually just be the light probe itself if it's entirely enclosed, which means that it can just shine in general. Or no, I've got it. What we instead do is we basically see how much the light overlaps the volume in each of the 3 dimensions, and we basically use that as how much we write into the octahedron. Right? Because we would know, we know the overlap in X and the overlap in Y. So at the very least, we should be able to do, that's the region of the octahedral map we write into is those TX and TY values, right? So there's probably a way to do that, pretty cleverly, right? I probably want to start not doing it that complicated, because that's some pretty fancy footwork. You know what else we could do is just do this stochastically. We could also just generate random points inside the light volume, and for a given point, then you obviously know which direction it is, because you can just literally do the subtraction between the light probe location and the point on the light that you picked. So maybe let's go the stochastic route first, where we just, and it doesn't even have to necessarily be stochastic. It could literally be regular. We could literally just sample regular points on the light source. But let's do that first, which means we leave everything as it is. We don't make any changes to this right now. But we do, on our pass through the light source, we generate a bunch of random garbage, and we sum those into the light. We sum those into the light specular. By the way, I have a question. Does our lighting now, by default, also... I'm sorry to get off topic here, but does our light basically also support specular now? Because we compute the specular map and the diffuse map, and I don't know if we send the specular map down or not. I literally don't remember if anyone actually submits the spec map, or if we only ever submit the diffuse map. Light depth sampler. We don't actually use that. Like, we never implemented that. That was going to be... So we did actually even think about that. Interesting. So the light color sampler is only sampling the diffuse map. We only send the diffuse map down at the moment. But we have the spec, right? So, like... when we link the sampler here... So we update both of them. The diffuse atlas handle and the specular light handle are both submitted. And both are bound. So we do have both of them. But we just don't use them. This code is so nasty. I really wish we had a way to read this better. We're gonna have to move these out to separate text files, I think, is the only real answer. I'd wanted to avoid having to do that, but it's obviously not gonna happen. So that's fine. I don't even think 4Coder gets worked on anymore, right? I assume at this point it's just not. It's just a non thing. So we'll probably have to deal with that at some point. Maybe someday we can switch to that 10x IDE thing. That seemed like a pretty good thing. I don't know. We'll have to see how it comes along. I'm not sure how it's going at this point, but anyway, if we have the light color sampler here, I guess I'm not sure where the light depth sampler comes in. Like, that was something we used to be doing, I guess, when we thought we were going to have to implement the depth part of it, but we didn't actually do that. So the light depth sampler is the fourth one. I think that's just the specular map, though. Because if you look at what happens here, texture 2 and 3, the depth is it's not that. Like, that's not what that is. So I think light depth sampler is actually the spec map. And I don't know why it's called that. I think we thought we were going to do that, or I don't know. I guess I don't really know. It doesn't get used. Right? I'm going to go ahead and say that that is just specular sampler instead. Because I can, because I wrote the code. And I'm going to just ask the question, what happens if you sample from the spec map instead of the diffuse map, right? I mean, why not? There's no particular reason you can't do that. It's just at the moment, everything happens to be sampling from the diffuse map. Now, they're the same dimension. So this is actually sampling from... What is this oct map interior UV dim specular versus UV dim diffuse? So we even compute the specular and then we just don't use it? I guess so. So at the moment, we actually compute 2 of these, but we only use 1 of them, I guess? We really need to clean this up. I don't know what the right answer is. I really was hoping we could just keep all the code in one thing, but unless I guess I go modify 4Coder myself, I could modify the source code to 4Coder probably. to actually format this. It's kind of impossible to read a complex shader in this way. It's complete garbage, right? Like you don't get any indenting or anything like that. So it's pretty impossible to actually use. And of course, because C++ is designed by people who have, collectively, if you sum them all together, 0.5 brain cells, there's no way to actually just like use included here docs here, I don't think. So we can't just put this in a separate file and then say, include this as a string. I think like I know people have actually literally even submitted proposals to do that, and I think it took them like many years to decide on it, and they ruined it or something. So I still don't know if we ever actually got that after 40 years of C++ specifications. Maybe that's in there now. I don't know. That would obviously be another solution to this problem. If you could just pound include a string, which is an obvious thing you would do in any language, but, heaven forbid the C++ Standards Committee allows you to include binary data into a friggin' executable. Anyway, so I don't know that we have much of a way around this, and this is really hard to read, so I'm not sure what we should do about that. We could add something that just loads these as text files. Or maybe someone can tell me if they ever frickin' got pound including strings into the frickin' language. But assuming they didn't, we're stuck here. And I just wanted to know, like, looking at some of this we can probably cut out, like I don't know what this is supposed to be, but this is a specular mixing function. I just don't know that we... I don't know how useful this would be to us, but it is a mixing function. Light V is the encoding of the light brightness. Light N encoding is, yeah, so this is, we can just rewrite this again. Like, it's just a reflection like, let's get rid of this just so we don't need that. Again, just trying to like clean this up a little bit so we can read it. I think standard embed got killed. Does anyone know how it's possible that the C++ Standard Committee is as bad as it is? Do they have some kind of pre-filter where they're like, we only allow programmers who literally have no idea what they're doing to contribute? Like, is that some kind of, like, did they work out a way to ensure that nobody who ever actually got something done in their life is on this committee? I don't know how they manage it. It's like, it's kind of amazing. If you could just figure out a way to invert the quality of the C++, like, most things can't be as good as the C++ committee is at being bad. Being that consistently wrong in and of itself is hard, because it almost means you know what the right answer is and then you intentionally not do it, because nobody can randomly be as bad as the C++ committee. They're more wrong than random would be wrong, right? Which means that they actually have a process that ensures that correct answers don't happen, right? Which is a different thing than just not having a process that ensures correct things happen. It's really kind of insane, and I don't know how it's possible. So they literally have some way of ensuring that good ideas cannot be added, as opposed to just not having a procedure that ensures that good ideas do get adopted, right? And that, it's almost worth studying, because if you could just do the opposite of what they do, you would have a committee that always makes the right decision. And so there is value, like, there's value to studying the C++ Standards Committee, because I feel like nobody else in history has ever come up with a system that guarantees that they will never make a good decision. That's almost as hard as always making a good decision. It's terrible. It's the worst possible thing you could be, but it's also educational because no one's ever figured out how to do something like that before that I know of. Like, no one's ever been able to make sure that they will never make a good decision. That's kind of hard in my mind, you know? I don't know. I think like Samo Burya or somebody should do a study on the C++ committee and be like, well, we don't know who to we don't know who to study to find out how to like solve the successor problem, right? But we do know who to study who is someone who has sort of solved it in the inverse. Like, they've guaranteed that nobody ever in the entire history, no one has ever succeeded in the C++ committee at actually making a positive improvement. That's almost the same as solving the successor problem, because if it was just random who was succeeding them, they would sometimes make a positive decision, right? Another way to say it would be if you could use the C++ committee as part of your language design process by asking them to pick the next set of things to add and then removing those from the things you consider adding, right? So, oh, yes, youngster Glenn just said exactly what I was sort of he got there faster. If you had enough C++ standards committees, all you'd have to do is design a language exclusively out of things they didn't use, and your language would be perfect, because they're guaranteed to only pick bad things. So if you know that all C++, right, like if you can, so they really have produced something very interesting. The C++ Standard Committee literally has a way of guaranteeing they will produce only bad language features. That in and of itself is actually useful because it means you can always just eliminate those from what you are designing, and your design gets better. They have done one thing for you, which is produce an entire spec of things not to do. Right? Inside constant pressure, you can read a file and return an array. I mean, maybe. I don't know that MSVC supports that yet, but it's possible. Like, compile time code execution, you could write something that would do this, right? But I don't know how far they are on actually providing that implementation. I have no idea, right? Yeah, like, metaprogramming makes this easy, right? If you can just do that, it's not a problem, but... Yeah. All right. Anyway, so let's take a look at what's going on here and see if I can answer my question, though, about what we're doing for lighting. So here in the now properly formatted lighting sampling call, you can see that we actually compute like the same thing twice that we don't really need to, because we don't change the dimensions of these two things, so it's probably stupid to bother doing that in the shader. We should just say that the diffuse and specular always have to be the same. But, you know, we still don't really know if maybe we want one to be more than the other. You could see, like, doing something different. Right, so, you know, hard to say. We don't really use C++, NetBuilder. We basically just use C. I'm more just complaining about the fact that you would think C++ would be better and I could go use it, but it never is, so I don't, right? I just end up programming in C because C++ is so freaking bad. But I would like an improved C. It's just, you know, no one's really made one, and please do not suggest languages to me now. I really don't want to have a gigantic flame when someone says you should check out X, and then I have to go out ranting about how bad X is. Okay. So when we look at this, we have basically computed both vectors, but we only actually, and you can see here we're computing like the locations of things, but we then need to do like a texel fetch, and we're actually, when we are interpolating these, we're actually interpolating the octahedral map in a more fancy way than I thought. Interesting. So you can see we're not actually doing like uh, a basic interpolation. We're doing like a fancier like radial, like semi-radial here. Do you guys remember doing this? Um, I don't remember doing this. I don't remember doing this, but all right. Um, so I guess we use something better than bilinear. I don't remember that we did that, but we do that when we interpolate the octahedral map, and all right. I mean, I guess I'm proud of us for that. Am I though? So I'm kind of interested now because now I don't even know. Um, what happens if we turn that off? Because I didn't even realize we were doing that. We must have played around with it at some point and then decided, oh, it's like better if you do that, right? And to be honest, I really just don't remember. So if we were to change that to using the old path, so we just, that's just the standard, that looks like a standard bilinear path, right? Does that actually matter to anybody? Because I can't imagine that it would. And to be completely honest, I don't really see a difference there, right? It looks like we can also just sample once. So this should give us like a completely... so is it maybe we only reload when we restart? But I don't think so. So that means I can take one sample. Am I looking at a totally different like path that we don't call or something? We should check at this shader again. Because I don't see any difference between any of those. Like this does not look any different than that, really. You know, not in a way that like I can perceive. Like it's probably different in some way. But so when we do sample lighting, no, it's calling. I mean, that's the code path. But it looks like we're doing a lot more work than we needed to, because it looks like if you literally just sampled, if you literally just use bilinear, this would just do the bilinear sample, right? Here's manually doing the bilinear sample. Here's doing something fancier than bilinear, and I'll be honest, I don't see the point. That looked fine, right? So you know, I don't know that we need any of that garbage in there. I mean, maybe we do, but like, I mean, once you actually get this stuff going, it just doesn't seem. I mean, yeah, I can see that that's maybe a little squarier. Yeah, I mean, you know. But part of that extra squarier is because we haven't addressed the other problem with the light not being added to the other elements, right? So, like, these guys don't really have that problem particularly much. So I'm not sure that once we fix it, we would even care about that all that much. You know? So I'm not sure I'm not sure we give a crap. I'm not sure we give a crap about that. But we can see, I don't know, can we see any difference here? I don't see any difference there. Does this actually work? Like, I don't even remember if we reload shaders. Like, let's suppose we said, like, oh yeah, hey, by the way, everything is like red always. That's just something that happens in the world. Well, we're reloading shaders, I can tell you that. So I don't know. I mean, I don't see a difference between the bilinear and the non. So you know what? We're just gonna say that that's it. I think we're turning that off. And I don't know, like, it seems like it's just fine as just a regular bilinear sample. I think that's probably fine. And this is, I think, mostly, again, like, I think we can fix that squariness in a different way. So I'm gonna go ahead and say, like, maybe we just don't care about this stuff. Like, maybe we just don't care about this stuff. So let's suppose we went here and we grimbled this particular Gronkus here. And this just became, you know, something. I don't know what the A value is doing there. I don't know why this is even returning an alpha value in the first place. That doesn't really make any sense. I don't know why any of this is a V4. It's just stupid. It don't make no sense anyhow. So probably this should all be V3s, right? Like what would the A value? What's the alpha value? There's no point to that. So this should probably be all BV3s, right? All the way down. And because I don't see any point to it, because what were you doing with what were you gonna do with that alpha, right? Like, what was the point of that? There's no point. So let's change this to do a V3 because we had to amplify it to not do that, which seems dumb. So let's go ahead and just remove all that garbage so that now we just have this. And let's see, we're probably going to get a compiler error because I probably, you know, chonked something out there accidentally. We'll probably end up at shader validation failed. Nope, we didn't. All right. So that's all fine and whatever, and that's good. And if I clean up the indentation here that forecoder munged, we can see roughly what this code is doing as well, which is, again, not particularly interesting. This is just indented too far for no reason. But now we're good. So we can see the lighting sampling here is just taking the light sample from the 8 neighbor light probes for any given pixel. And because GPUs are so ridiculously fast, that's just fine. Well, no, more specifically in forecoder, if I told it to indent, it would indent. But the problem is it thinks this is a string. So it's going to do things completely wrong, right? That was the entire part of the problem. Normally, it just indents everything for you automatically, and you don't have to do anything, right? But in here, and we could add a function that just, like, moved things around in here, but really what I want is for it to just indent these as if they were code. And unfortunately, there's no way to tell it to do that at the moment, which is partly forecoder's fault, but it's partly C++'s fault for sucking. So anyway, when we do this sample, we could, in addition, take a we now have the specular sampler here, and we could call this, instead of like color sampler, I could call this diffuse sampler, so that it's clear what's actually happening here, right? Diffuse sampler. And we would then change this to diffuse sampler, like so. And I think that would give us the exact same behavior as we had now, only the like nomenclature actually lines up. So let's think about specular here, because I figured we can now actually take the specular sample as well. We could instead, like, and let's just do it directly. We can do a specular sampler sample specular UV. And now that will just overwrite our diffuse sampler with a specular sample, which would make everything unpleasant and shiny if any of this works, which it might not. But you can kind of see the difference there, right? So everything is like very reflective now, and nothing is smooth like it was before, right? So the spec sample is not going to be going in the right direction right now. So we have to kind of change that a little bit, but I would like to change it just so I can see what kind of specular lighting we have, because we actually kind of have spec lighting now. We're not actually using it. We probably should, right? So yeah. So when we look here, we've got, we're going to sample the lighting, right? We do the lighting sample, whatever, blah, blah, blah. We need to take the light direction, which I guess is this. So that's wrong. Kind of. Is it? I mean, no, I guess we would sample them both from the same place. Would we? That's probably not true. So here's us mapping it into the octahedron, where we're actually sampling. So the problem here is that you would have two of these, right? Because one of them's going to be like the going to reflect off the I vector, right? Psara Crocata, you can do that if you want. In 4Coder, you would just have had to have actually created that function, right? Or rather, bound that function to something. I like manually created all the stuff that is bound to the keys in my version, so I don't actually have anything bound to that, right? It would be very easy for me to add something like that, but because literally you never need that for any reason, I never added it. I never added a binding to do that. So, you know, we end up in this situation. I could go add one, but really I think I don't want that. I want to have this auto-indented like everything else. So I probably will just move them to separate files at some point. Probably. So, you know, I don't know. But anyway, the point is, so the specular version of this, I think now we would just need to have the reflection vector, the I reflection vector, would have to be somewhere in there, right? So at the moment, when we compute this, we take the... Yeah, right? You can actually see it. It's like right here. That, for those of you who know what you are looking at, that is literally the reflection. right? So if we change to using the actual reflection vector, we would get this, which, hey, looks a lot like specular lighting now, as you might expect. So, right, you can see it travel upward. You can even see it smear out across the surface there, right? Exactly like a wet surface would do. So we certainly could now have it, we could now have lighting that had actual surface properties, meaning things could be like part spec, part diffuse. If you want, you could blend those two together. Which seems valuable because you get kind of some of those nice effects, right? Like that. Recyrillic, I was wondering about something like that, so I would like to know what you're talking about. So let me take a look. You can use a macro like poundify in shader code A, pound A, and then on char star shader equals shader code, insert shader here. The shader code interesting. Interesting. That seems like a good trick that I might try. Actually. Yeah, no, I would definitely try that. So I'm interested in the we might try that. That's a good idea. I like that trick. So I don't really know what to do about this exactly. So I think what we probably want to do is be able to pass down the two octahedral values here. We want one for each of them. So we would want this to be like the world end is one and the reflection vector is another. And this function would want to be able to be called for either. So like this would need to be a thing that you could call, right? And you would want to be able to get the v2 that you were using for sampling here, and you want to be able to pass like both of those in. So you'd want to have a thing that was like oct from or something. And we'll, you know what? After I'm done with this, real quick, we should try that that pound define trick. I like that. Solve it with a macro. So if you pass in a normal, I guess we'll just use R here, right? Then you get oct out like this. That seems fine. And then in here, we would just say like v2 oct equals oct from world n, right? Or R, right? And so we could get both now. So that we could get both the reflection vector, and maybe I call this reflected so that it's a little clearer what the heck R is. And then we have like the diffuse oct and the spec oct, right? We pass them both. In here. So hard to edit anything as a string. So this is why I want to fix this if I can. It's really hard to edit when it's all a big string, and F4 coder doesn't think it's a real thing. There. So now we have both of the two octahedrals, the reflected and the diffuse, and they would come in here as diff spec and diff oct. So that when we look at where oct is actually happening here, it's literally just that one. So I think it's just this. Don't ask me why I wrote that backwards. So maybe that does both samples. Maybe. I ain't even know. But we'll find out. So if we look at, our vague test here, it kind of looks right. I mean, this not particularly accurate testing here, but okay, looks a little bit like something. Not very good, but it looks like something. So we can here take both samples. So here's the diffuse. Here's the spec. We have both of them, right? And we could use those to produce the results. So we could do like diffuse plus specular to produce our results. And normally what you would do is we'd have a material parameter here. We don't have one right now, but you'd have a material parameter that would tell you which you had, right? Like whether a surface is particularly diffuse, whether it's particularly specular, right? And so for right now, we'll just pretend everything's like half and half. Because we don't have a material parameter, but eventually, maybe we get a way to send something in there to, to say like you're gonna, put those together. I don't know. So anyway, like I'll just pretend we have one. I'll put it to do like it'll just be like, hey, yeah, there's like a spec level, spec shift. I don't know what this would be, but like material. It's called material, and for now it's like half and half. So we lerp between these two like that. And so this is just going to be like it's half and half. There's no rhyme or reason to it. It's just that's what it is. And if we wanted to, we could use that to like control some aspect of what these materials look like. As it is, this just kind of makes it look maybe a little bit better because you get a little bit of a feel like that just looks a little nicer. It just gives, a little bit of character to it. So I can't see that it hurts to just turn that on everywhere. And maybe that's all we actually ever do. Maybe we don't have material parameters because it's not like it's real spec. Like it's not like we're actually computing at higher enough resolution for it to be like bounce reflections, right? We don't really do that. But it's all right. So let's see the shader code thing here that was suggested. Let's see what happens with the shader code trick. So the suggestion was to basically do something like this, like say, hey, there's something called embed shader or whatever, and you include the code, and it just puts the code as a giant string. And then the idea here would be that you would say, well, okay, instead of the here doc version that happens like this, the suggestion was, well, you just do that, and you see if that works at all, right? I'm not optimistic that'll work, but who the heck knows? Maybe it will, and in which case, if it does work, that would be cool. Right. So now this is our gigantic shader that is all included as actual code. And in theory, I could come in here maybe and indent it. And it would indent, although it looks like it's kind of like far because it indents to that as the margin. But I could maybe do something like this, and that way it would pull it back a little bit further, and that would be fine. But then it all like indents correctly, which is what I want. So that's like would be way better if this actually compiles. I don't know if it will, but we'll give it a shot. No errors. Shader validation failed. Did I accidentally clip something out? Let's look at the errors. I don't quite follow what has gone wrong here. Is it this that it's complaining about? There's no other token pound in there except on those depth peel pound if. So yeah, the pound ifs wouldn't come through, right? So like that probably doesn't work. I mean, I don't know what the spec for the string eyes operator, which is that thing. I don't know what that does with this. I don't know. But it does look like it don't work, right? Probably just because of those. I mean, probably it would be fine without those, I guess. I mean, we can do the test. Like, I'll have to undo those changes because we actually need those pound ifs. Like, I don't want to get rid of them, right? But we can certainly try to see if it would work without that. So it is actually that is actually the problem, right? You can't have pound ifs in it. So like we could try to work around that a different way, but I mean we do need we compile this shader in a couple of different ways, right? And like maybe we could change kind of how we're doing that. So but for now, I think the raw string literals is all we really would have, and we just have to go change the four-quarter source code to stop treating them as strings. So I think that's basically it. Anyway, back to our story. So I'm kind of glad that we can put spec in there as well. That's pretty cool, in my opinion. I think maybe the lighting is still a little too bright right now for my tastes. Like I think we might want to like it's not as spooky as it should be. Like things are just too bright at the moment. I'd like to, I like to keep things spooky. I think at some point, if you end up in a situation where you've despooked things to a certain level of spookiness that is sub spook, it's less spooky than it should be, then you run the risk of having a completely unspooky game, and that I don't ever want to really be in that zone. So let's just try to keep it a little spookier. So first of all, I don't know what we're doing with the outsides, but I guess like the garden. I don't know what any of this stuff even is. Let's be honest. I don't remember why we named certain of these things what we named them, but I'm curious, like, okay, so if I remove the lighting from outside, it still has, like, the flat lighting from moonlight, right? Which, is what we would expect. That's probably a little too bright. Probably would be my guess. So that probably wants to get fixed as well. This looks like appropriately spooky. These are maybe a little too bright. Let's go take a quick look. Sorry, I know this is not what I said I was going to do, but you gotta do things when you do them. So when we're not indoors, when we are outdoors like this, we add this light in here, and it should probably be just a lot dimmer. I don't know. It should probably still be like brighter than the apron, maybe, or maybe we should just add a light to it if we want. I don't know. That seems better. So I think we're now just down to needing this to rasterize more properly, so that we don't get the splotchiness. I think is the only other thing we want to do. And the question is just, do I want to do that now or do I want to do that next weekend? I think I want to do that next weekend because I'm going to want to make dinner and stuff. So I think we're down to just that. The splotchiness of this we can fix and should fix. So I think we're going to want to do that, right? I also don't know where we are at on flickeriness. So is it really necessary to be at 6 right now, or have things gotten to the point where actually we don't need it to be at 6 right now? And I don't know the answer to that question. Let's drop it to 3. It doesn't look very flickery at 3. What's it at 1? Am I seeing this right? Did we make some kind of mistake where, like, why is it not flickering? Something's broken. Oh, right. I went the wrong way. I'm like, it should be. Ugh. This will increase the flickering. There you go. I'm like, God, that was just weird. So, so it seems like that is kind of our flicker floor, right? Is like around 6, so it's 10 frames flicker floor. Which would suggest if we could speed up the raycasting a little, we could get probably to this level, which is a little flickery, but is closer to full speed. It responds a little bit better. So I think this should probably be our target, is to deflicker this, which I think we can do. I think we can manage that. So yeah, we just need light rasterization. I think I'll save that for next week, but I think we're in really good shape. The lighting is so darn good right now. And really we just need to fix sort of the squariness of this, like the responsiveness with, I think forward rasterization of the lights is the right way to start with that. We might need something else in there. I don't know exactly. So I don't want to promise that's going to fix it. We may have to do a little more work than that. But I think that's a large part of it. Because one of the reasons, as I've mentioned before, one of the reasons you get these square artifacts is when the light isn't properly represented. When you get an unnatural clamping to 0 on your linear interpolation, you get this kind of thing. So I could easily see just rasterizing the light fixing this, because right now it's not a smooth fall off like it should be, because we're not doing that, right? So I don't think I don't think we're far from good. This is looking pretty awesome, to be honest. And I think we can deflicker this. So right now, our main problem is if if we wanted to crank the rate count up a little bit more. And don't forget, we're on the CPU. Moving this to the GPU would get us a huge speed boost as well. So we can always just target that as something we do later as well, to solve the speed problem. So we're very conservative right now because we're doing everything on the CPU side, and the GPU can do a lot more flops, right? So yeah. Excuse me. Also, you could just run it on a faster machine. Run this on a Threadripper, and you could count or even just a machine from today, right? And it would totally stomp this thing, for sure. So, yeah, the ray weight is the ray count here. If I turn that up to 16, the game will be slow, but it should be about as stable lighting wise, right? So hopefully now we don't really see in the flicker, which I don't. Even in here, the flicker is pretty minimal. Like, you would not care about that much flicker. So I do think if we can just double our raycast, which I think is probably doable even on the CPU side, definitely doable on the GPU side, I think we would kind of just be done. I think we would kind of just be done. Yeah, I mean, this lighting is just like very good now. The only thing that's objectionable is that rasterization artifact, or that lack of rasterization of the light source artifact. I mean, that's just really freaking good. I'm sorry, but it is. Okay. So now we probably call it a day, and we tackle the forward rasterization of the into the light probes to get a nice smooth distribution for small moving light sources like that. I think that's it, and then we're good. I do want to see what happens if we turn off the lighting again now. I mean, that's just really good. I mean, right? I mean, that's just like very good. Yeah, I mean, so I think we're basically done. I mean, I really think we just have to clean up that, figuring out how we get the probes for overlapping probes like that. We just got to fix that. And then I think maybe we just rewrite the cast to be based on array bundles, because I think it'll be a lot faster. We may be able to get our 2x there, actually. But that is just very responsive. Not very much flicker except in the really dark areas, and I'm okay with that. And just looks fantastic. Um, so like I also would wonder, like, so where's our snake? Where's I don't know how this. I guess this world gen is stupid and bad. And that probably is the thing we'll be cleaning up right after we clean up the world storage, because now we know we don't have 2D. We can cut out a bunch of code from that. I mean, we don't have 3D stacking. But where's the thing that creates the, like, we have a thing that creates snakes in dungeon areas. I guess it literally does it right here. So I guess if I wanted to, I can just add this to something else. So if I wanted to add this to, I don't know, like bedroom A, would that just work? And the snake pattern has a light on it, I think. Doesn't it? Or maybe it doesn't anymore, but I thought it did, at least at one point. Add piece light. So if it's got a light on it, that 1.0 light's going to be way too bright. We already know that. But does that add a snake somewhere? Yes. So like I said, way too bright, but we know how to fix that. I am Seabass. I agree with that assessment. So the skeleton dude, of course, they get stuck in the corners. Sorry, skeleton man. Maybe we should just make them have less pieces. Anyway, yeah, like, I mean, I think this is pretty solid. We really have to get our poor snakes. They all lock up like immediately. Oh well. All right. I'm pretty happy with all of this. I think this is all great. maybe the standard lighting, when we add this back in now, the standard lighting pattern, probably we should just make those lights less bright. Again, because of the spookiness issue that I spoke about before. And we can return to this nonsense here. Let's make things half as bright and go from there. So I think we're all good now, and I think we'll call it a day here. But this creates some like different light colors, which was just kind of a nice touch. I think this looks fantastic. I'm really happy. So basically, we'll just fix the occlusion problem here, which hopefully will get that light, that kind of light, looking a lot better. And then we'll just assess. It might not. If it doesn't, then we might have to take some other steps to figure out what we're going to do to solve that problem. But I think that may just be the bug. That may just be that sort of skipping problem is because of that bug that we know about. And so I think if we just fix the bug, we may just be done. And then we move on. So that's it. Happy fun day to everybody. That's all there is. I'll be back here next week to fix that bug, and we will cross our fingers that will basically be the end of the lighting debugging. We would like to probably rewrite that routine to be Ray bundle based, so we may want to spend another weekend on that. But that, I mean, hey, that we may actually now have legit good lighting. So yeah, at some point, mine Mark 42, the feedback issue is because something in there is measured as a proportion, and we just weren't thinking about it that way for some reason, right? So setting all of our numbers to be normalized between 0 and 1 fixes that issue, and it's really just a bug in our thinking. I don't think we actually have a bug in the problem. I don't think there is a bug in the program. I don't think there is an actual feedback bug. I think it's literally just a bug in our thinking, right? The values are all percentages, and I guess I'm missing a place where that propagates through. Somebody who knows more about lighting would just know that. They just be like, oh yeah, like because you wrote this part of it this way, it means, the light values have to all be percentage of the maximum light value or whatever. And I'm like, okay, right. But as you can see, we can get exactly the same result just fine, completely stably. So I don't know exactly where that percentage is, but I don't think we have to do any work to fix. In other words, I don't think there's any problem. The feedback is not there. It's just because of a units issue. So we don't actually have to fix it. It would be nice to understand it. But we don't actually have the bug. I don't think. Wylam, I don't know. I don't think it's that simple. I think it's more complicated than that, because it would not explain, like, it doesn't really explain why simply normalizing the values between 0 and 1 automatically fixes that, or rather, it also doesn't explain why you could set them to things that were higher, like 1.3, and not have the problem, right? Like, so it's probably slightly more complicated than that, but I mean, that's obviously part of it, because we know that because it operates over several frames, it can have that kind of feedback, right? So any bias in the system will produce that, but we don't really know why it's sensitive to the units in that way. Because we now are essentially producing the same values, we just multiply by 10 at the end, right? So we're still, we produce the same kind of light values. They just don't feed back on each other because they're normalized between 0 and 1 to begin with. It's not immediately intuitively obvious to me why that unit change, why representing things between 0 and 10 versus 0 and 1 has that behavior. Obviously, it's because numbers significantly greater than 1 can feed back in some multiplicative process. I just don't understand what I don't understand exactly where that is taking place, right? So representing the lighting as numbers between 0 and 1 instead of between 0 and 10 completely fixes the problem, even if you then multiply by 10 to get the exact same values back, right? That's why I say, like, maybe we just ask Don Mitchell to come solve the problem for us, right? Because he would know and we don't. So, anyway, that's it for today. Thanks, everyone, for joining me. I will be back next weekend when we will try to fix the problem with lights occluding sample probes, because we definitely have a problem with that. So I will be back for that. Until then, have fun programming, everyone, and I will see y'all on the internet. Take it easy, everybody.